An experiment staged by the outstanding Russian physicist, Peter Lebedev, was intended, for instance, to prove the existence of light pressure by demonstrating the effect of a light beam on a metal blade, and also to compare the obtained value of this pressure with the value predicted on the basis of Maxwell's theory. The most difficult part of the experiment consisted in creating the necessary conditions to ensure the fulfillment of the rules of abstraction. There was no special difficulty in observing the rotation of the experimental blade after switching on the source of light. Yet it was just here that an error might slip in, since the blade could be caused to rotate by other factors as well, such as radiometric forces, the forces of gas convection, etc., the more so as they exceeded many times the weak force of light pressure. It took not only the experimentalists' resourcefulness in developing the appropriate apparatus, but also called for a profound analysis of the nature of convection and radiometric forces. Hence, attempts to prove the existence of causal relations may lead to the discovery of new phenomena, to new interesting and unexpected explanations pertaining to the conditions under which the main investigation is carried out, and, finally, to the improvement of experimental equipment, as the scientist always tries to envisage its response to various side effects. It may so happen that the forecast of a causal relationship does not come true under the given set of circumstances. Does it mean that we should question the principle of causality in general? Of course, not. In that case we are faced with this alternative: either our prediction of a causal relationship is not correct and the existing correlation is the result of other indirect links, or the causal relationship does exist, but the experiment or the observations give wrong results due to the presence of unknown interfering factors. In both cases the principle of causality leads to new problem and stimulates new discoveries, often quite unexpected. Hence, the principle of causality not only fulfills the functions of explanation and prediction, but is also of great heuristic importance. To assess correctly the heuristic role of the principle of causality, one should take into account the fact that the scientific discoveries resulting from the evaluation of specific conditions, the revelation of hitherto unheeded factors, the rejection of ungrounded assumptions, etc., are of 10 more important than those sought by scientists in their attempts to explain or predict one or another event. It may seem all the more paradoxical as conditions, according to our own assertion, are inessential for the causal dependence to the extent making it possible to disregard them altogether. Yet the dialectics of these two aspects of objective reality consists in that the conditions inessential for a given causal relationship may prove highly essential for another relationship. One of the main objects of criticism leveled against dialectics by its present-day opponents is the law of the unity and struggle of opposites. According to an ancient and at the same time the latest argument against dialectics, an objective contradiction is incompatible with the logical principle or law of contradiction, whereby two opposite statements cannot be true if they relate to the same time and to the same content. Accordingly, an object of reality cannot possess two mutually excluding properties or be in two mutually excluding states in one and the same respect. It should be noted first of all that the term dialectical is by no means applicable to any opposites or any contradictions. We can only speak of contradictions within the framework of a concrete relationship in which two phenomena, two aspects of one and the same object, can be regarded as opposite and mutually contradictory. Accusing dialectics of speculativeness, scholasticism, and absence of any scientific value, positivist philosophers and other modern opponents and interpreters of dialectics refer to a vice which is absolutely alien to Marxist dialectics. The concreteness of the law of the unity and struggle of opposites is violated each time its critics tear apart the two inseparable aspects, the unity and the mutual exclusion of opposites. One cannot speak of the opposition of certain aspects of an object or a phenomenon until after their unity has been established, the degree of their opposition corresponding to the degree of their unity. It was senseless, for instance, to speak of the opposition of the Sun and the Earth before it was found out that both of them are two celestial bodies belonging to one and the same planetary system. Likewise, it is senseless to speak of the opposition of science and, for instance, art till we establish that both of them have the same nature as two forms of social consciousness. Hence, there are no and cannot be any objects or phenomena which are absolute opposites, opposites in general, in the abstract sense. Conversely, there are no and cannot be any two absolutely identical phenomena. Such identity from the dialectical viewpoint is also abstract. Any knowledge will be abstract, partial, incomplete, if it does not properly reflect the contradictions inherent in the object under investigation, if it is presented as something immutable, frozen, lifeless. Lenin has closely linked the question of the concreteness of knowledge with the question of the mutability and contradictoriness of the objects and phenomena of reality, as is seen from his following emphatic remark: cognition is the eternal, endless approximation of thought to the object. The reflection of nature in man's thought must be understood not lifelessly, not abstractly, not devoid of movement, not without contradictions, but in the eternal process of movement, the arising of contradictions and their solution. From the positivist viewpoint, this statement is nonsensical. Limiting the subject matter of philosophy to the analysis of existing scientific knowledge, and this mainly in terms of its correspondence with the standards of formal logic, positivism has once and for all defined its stand in relation to contradictions. Contradictions are only possible in thinking and therefore must be removed from our knowledge, as their very presence testifies, according to formal logic, to the falsity of at least one of the opposing statements. Dialectical contradictions in nature and society differ from the so-called logical contradictions. In contrast to formal logic, which understands contradiction as incompatibility of statements, dialectics regards it as conflict of opposing forces or tendencies. Such dialectical contradictions can be exemplified by the phenomenon of class struggle, the relationship between nature and society, etc. In thinking and cognition, the concepts of dialectical and logical contradictions coincide, i.e., the dialectical contradiction assumes the form of the logical one. It is important, however, that one should distinguish between the role of contradiction in the development of cognition as empirical phenomenon, on the one hand, and the consequences of contradiction for concrete knowledge, i.e., for cognition in the logical sense, on the other. As regards the former, the revelation and resolution of contradictions is the motive force of cognition. As to the latter, a contradiction in the logical structure of knowledge is always objectionable, as either one of the two contradicting propositions within a given system can be used for deducing logically correct statements. Hence, it is not logical contradiction, but the search for the ways to eliminate it that constitutes the source of the development of scientific knowledge. The logical principle of concrete identity, the identity of opposites, was for Marx the main logical criterion of concreteness in the approach to the objects and phenomena of the objective world. It was this approach, according to Marx, that made the difference between the trivial, uncritical description of phenomena as they appeared to everyone and their theoretical comprehension. The dual nature of the commodity was by no means Marx's discovery. Even before Ricardo and Smith, any man in the street knew quite well that a commodity had use value and exchange value, or, in other words, that it could satisfy some human need, or be exchanged for another commodity, more necessary at the moment for a given owner. The assertion that the commodity is a carrier of use and exchange values has nothing in common with the theoretical proposition disclosing the nature of value in general. The former is a mere statement of two isolated abstractions in no way connected with each other, whereas the latter proceeds from the understanding of the use value of a commodity as a method or form of the manifestation of its own opposite, the exchange value, or, more precisely, simply value. This concept represents a transition from the abstract to the concrete. Consequently, knowledge cannot be sufficiently concrete unless it reveals some general aspects and properties of the objects and phenomena of the objective world, their essence, main contradictions, content, necessity, etc. Yet it is precisely these aspects and properties which constitute the subject matter of philosophical investigation proper. Therefore, philosophical concreteness is not a contradictionary in adjecto, but a profound theoretical concept. As it turns out, the knowledge given us by physics, chemistry, biology, geography and other special sciences should also be concrete from the philosophical viewpoint. Without such abstract categories as quantity and quality, chance and necessity, essence and appearance, etc., the concepts of atom and elementary particle, organism and living cell, man and society turn out to be insufficiently concrete. There is yet another important side to this problem. If we leave out of account the above categories, any scientific knowledge will only be testable within the scope of the links and relations that have already been revealed. In other words, the test will be confined to examining the empirical content of our knowledge, the object or phenomenon in interest being isolated from other objects and phenomena, and to establishing logical links between this empirical content and the theoretical knowledge already available. Hence, the possibility of a comprehensive test of any knowledge for scientific value and authenticity will be ruled out altogether, and, consciously or unconsciously, new concepts or theories will be left exposed to eventual criticism. Knowledge which has not passed through the crucible of a philosophical trial is not only vulnerable to critical attacks, but also liable to various distortions and misinterpretations. Here is an example. Before the establishment of the contradictory nature of light, its complex quantum mechanical properties, it would have been impossible, as we are fully aware now, to adopt either the wave or the corpuscular theory. Each of these theories could have been tested by corresponding experiments, yet these experiments contradicting one another would only have been regarded by the adherents of the rival theory as a temporary misunderstanding. The way of abstract identities leads away from, but not towards dialectics. Dialectics unfolds the analysis of concrete, living objective contradictions, whereas eclecticism, being in fact a counterfeit of dialectics, is engaged in the arbitrary combination of any opposites and identities. No better appears to be the alternative solution to the problem of contradiction offered by the representatives of the Frankfurt School. This solution, in contrast to the one proposed by positivism, is based on the absolutization of contradiction and negation and on the rejection of any identity whatsoever. The approach of the Frankfurt School, which is distinguished by utter disregard for the concreteness of the categories of identity and opposition, can be well illustrated by Theodor Adorno's proposition concerning non-identity. According to him, identity is the enemy of all that is factual, single, particular and, strange as it may seem, concrete. Concreteness, as it turns out, can only be saved through non-identity. The trouble, however, is that identity itself in Adorno's interpretation loses concreteness and turns into something lifeless, static, and absolute. Yet the identical, as has been pointed out by Hegel, includes the necessary seed of distinction, discord. Already in his Phenomenology of Spirit, Hegel came out against the understanding of negation as activity consisting only in refuting, nullifying the attained result. In the preface to that book, Hegel calls true that thinking which emerges in the process of development as a definite negative and therefore as some positive content. Adorno's negative, by contrast, remains abstract and lopsided, pathetically inferior to Hegel's profound concept, though, according to good Adorno, Hegel has failed to rise to the required level of thinking. Adorno interprets Marx in a similar manner, making special effort to find in his works everything related to the negative or negation and counterpose it to the positive or negation of the negation. In point of fact, the only difference between Marx and Hegel in the interpretation of identity and distinction, positive and negative, assertion and negation, is that Marx had placed all these categories on a materialistic basis. Freed from speculativeness and abstractness, they have acquired new forms of concreteness and preserved at the same time their interdependence disclosed by Hegel, who has correlated each pair and regarded it as an indissoluble unity. The creator of negativist logic, which is full of contradictions, writes Soviet scientist I.S. Narsky about Adorno, manipulates, like Proudhon, static antitheses, such as society and nature, democracy and technocracy, history and theory, criticism and apology, process and system, action and cognition, practice and reflection, humanism and scientism, discarding, though, almost any one of these alternatives just as easily or turning them into arbitrarily interpreted symbols. His method is anti-dialectical, dialectics with Adorno ceases to be dialectics and turns into the metaphysics of the rigid models of non-identity. It stands to reason that the exposure of trivial contradictions can little contribute to scientific investigation except by bringing in a few odd empirical details. Yet even these meager scraps of knowledge reveal their utter uselessness when it comes to molding them into a single concept. Just imagine for a moment a toy factory run by an eclectic in accordance with his theoretical notions. The toy's hops would be cram full of little monsters having an ear instead of an eye and an eye instead of an ear, a kneecap on the shoulder, a frying pan instead of a hat, gloves instead of shoes, trousers instead of a shirt, etc. This comparison, though, perhaps, a little too blunt, is by no means far-fetched. Of course, from the viewpoint of logic an ear and an eye, a shoulder and a kneecap are opposites in a way, just like the right and the left eye, the right and the left foot, hand, etc. Each object is the opposite of another object in some abstract sense. It would be absurd to engage in studying such contradictions without specifying the concrete relationship within which such contradictions are considered. In his critical analysis of Dühring's book, Engels wrote that his opponent's views on the question of contradiction can be summed up in the statement that contradiction equals absurdity, and therefore cannot occur in the real world. People who in other respects show a fair degree of common sense may regard this statement as having the same self-evident validity as the statement that a straight line cannot be a curve and a curve cannot be straight. But, regardless of all protests made by common sense, the differential calculus under certain circumstances nevertheless equates straight lines and curves, and thus obtains results which common sense, insisting on the absurdity of straight lines being identical with curves, can never attain. Referring to the universality of the laws of dialectics, its opponents allege that dialectics can prove or confirm anything in the world, it can be used to justify any political act. Since the laws of dialectics are applicable everywhere and at all times, they cannot be of any help in discovering something new. Herbert Feigl, who honestly confesses to having not read a single Soviet publication in philosophy over the past few years, regards the laws of dialectics as hackneyed banalities. The vague principles of dialectics, according to Feigl, are handicapped by Hegelian logic consisting, in fact, of illogicalities. They are scientifically useless both in terms of ontology and methodology. Dialectics, in Feigl's opinion, adds nothing new to the special solution of the mind-body problem or the problem of the corpuscular wave dualism. All that is needed to solve such problems is the good old two-valued logic plus the required natural scientific data. The slogan about the transition of quantity into quality, writes Feigl, is just as vague as the triad, or the negation of the negation. No Marxist philosopher would deny the universality of the categories of dialectics. The crucial point is the understanding of this universality. From the Marxist viewpoint, the universality of categories and laws consists in that they reflect the processes and phenomena in nature, society, and cognition. It does not mean, however, that the laws of dialectics are applicable to any situation regardless of conditions and that they exist outside and independent of the corresponding phenomena and processes to which they relate. The law of the interdependence of quantitative and qualitative changes is very concrete for all its universality and abstractness. It does not apply to any quantity or quality, but only to the quantity of a given quality. It means that not any, but only strictly definite quantitative and qualitative changes can be linked in a scientific context. The concrete unity of the quantity and quality of a given object is known to be reflected in the dialectical category of measure, which lays special emphasis on the concreteness of this unity. The quantitative changes of a given quality are restricted within the limits of a given measure, beyond which the unity under consideration breaks up and is replaced by another unity having its own measure. The concreteness of quantity and quality accounts for the relativeness of the distinction between quantitative and qualitative changes. It is only in relation to a given quality that one can speak of certain quantitative changes. Outside the bounds of the measure, such a counterposition becomes senseless. The number of the electrons on the outermost shell of the atom is directly related to its qualitative characteristics, to the quality as a whole. Yet this number does not affect the aggregate state of the matter, which includes the electrons under consideration. We do not mention here the trivial approach to this dialectical category exemplified, for instance, by an attempt to link daylight illumination with the number of stars in the sky. Proceeding from the abstract logical pattern advocated by the opponents of dialectics, we might say that any quantitative change in general involves one or another qualitative alteration. Take, for instance, the budding of leaves on a tree. The appearance of a new leaf on a branch is in itself a qualitative change. It involves the emergence of a bud, the concentration of chlorophyll, the absorption of light, etc. One might even speak of many qualitative changes. Similarly, the evaporation of several molecules of water from its surface, which brings about but a minor quantitative change in the volume of liquid in a vessel, is connected with such a qualitative change as the process of evaporation. The same quantity of molecules could have been removed from the same volume by means of, for instance, a sprayer. Can we indeed speak of quantitative and qualitative changes in this latter case? If we do, we shall make a common, even a typical mistake which leads sometimes to serious misunderstandings. Of course, if we speak in an abstract manner, the elimination of a certain amount of molecules is a quantitative process. But in relation to what? This is just the point, since the principle of concreteness calls for a very definite reference system without which any scientific analysis turns into nonsense. Whereas the aggregate state of liquid in a vessel does not change, molecules pass into a new state, acquire a new quality, the humidity of ambient air increases, etc., i.e., qualitative changes do take place, but in a different system of relations. The law of the interdependence of quantitative and qualitative changes would indeed turn into commonplace if we did not define in each particular case the relationship between a certain quantity and a certain quality, i.e., did not determine the system the development of which is the object of our analysis. Taking exception to the law of the transformation of quantitative into qualitative changes, Hermann Wetter writes that if the new quality were of a higher order, it would be bound to have something which cannot be explained in terms of the laws of the lower order. That means that the effect would be bigger in some respect than the cause, or, to put it another way, it would have no corresponding cause, at least with regard to the increment. Consequently, according to Wetter, the law of the transformation of quantitative into qualitative changes does not explain anything, it merely describes the transition from the old quality to a new one. As has been pointed out above, the laws of dialectics, though universal by nature, are not confirmable under any arbitrary set of conditions. They are operative within quite definite epistemological limits and become senseless beyond them. In other words, they can be falsified in principle, if we come across a sufficiently large body of contradicting facts. The absurd contentions that the categories and laws of materialist dialectics are trivial and unscientific derive from sheer ignorance. Such contentions are based on the subjective interpretation of dialectics and have nothing to do with its true nature. In most contemporary concepts of Western philosophers claiming to carry on the dialectical tradition, dialectics is replaced by eclecticism, the semblance of dialectics. To sum up, philosophical knowledge represents all forms of scientific concreteness, empirical, theoretical, and epistemological. It can be confirmed experimentally, given conditions for appropriate abstraction, and it can be falsified outside the limits of the objective field. Philosophical knowledge is theoretically concrete in the sense that it rests on the theoretical foundation of modern science, formulates its laws and provides answers to philosophical questions prompted by the development of science itself. Finally, philosophical knowledge is concrete from the epistemological viewpoint in the sense that each dialectical category and law is based on and relevant to the entire system of philosophical knowledge in terms of its logic and history. 4. Materialistic Dialectics and Special Sciences. By Igor Naletov. The nihilistic attitude towards philosophy and towards broad theoretical concepts in the period of the inception of positivism is closely connected with the stormy growth of empirical sciences in the late 18th and the early 19th centuries. The universal enthusiasm about their remarkable successes created an illusion that all mankind's problems without exception could and ought to be solved exclusively by the methods of natural sciences, which not only provided the exhaustive explanation of phenomena, but also predicted the existence of unknown phenomena and thus opened the way for new discoveries. Of special interest to us, however, is the connection between this philosophical nihilism and the boom of empirical investigations. This question is the more topical as in our time, too, the extensive development of empirical methods of investigation in one or another scientific field brings about a very similar phenomenon, a certain estrangement, if not downright victimization of philosophy. As is commonly known, empirical investigations usually aim at studying individual, sensually perceptible objects and phenomena of reality. Besides, the sphere of empirical investigation includes inductive generalizations and even the formulation of empirical laws. Most researchers associate theoretical knowledge with a higher level of abstraction, with the explanation of empirical laws, revelation of their links with other laws and existing theories, i.e. with their theoretical substantiation, as well as with the discovery of new laws which do not always lend themselves to empirical interpretation. The very nature of empirical knowledge, like that of applied knowledge in general, accounts for the fact that the scientist engaged in concrete empirical investigations is seldom forced by the specific problems he studies to concern himself with philosophical generalizations. At any rate, the logic of his research does not lead him to philosophical concepts of universal significance. It does not mean, however, that a natural scientist does not concern himself with philosophical problems and is in general far removed from philosophy. Even in a purely empirical investigation, a scientist cannot make a step without adhering, for instance, to the principle of objectivity. His task consists in excluding the effect of the subjective factor, i.e. the influence of his own manipulations, particularly of his personal perception and his individual experience from the conditions of his experiment or observation. Every experimentalist knows only too well the difficulties involved in the fulfillment of this task, as well as the severity of the requirement for the purity of the experiment. Not every scientist, however, is fully aware of the fact that this requirement does not stem from the nature of his specific investigation but is of general methodological significance, i.e. that it is a philosophical principle. Similarly, a scientist cannot disregard the principle of causality or determinism from the viewpoint of methodology. The experimentalist's work largely consists in a search for the causes of the event or phenomenon under observation, or in defining its possible effects. Here, too, the patterns of his thinking and experimental activities are predetermined methodologically so that he proceeds from events to their causes, then to their consequences, conditions, etc. In such standard situations a scientist relies on the available philosophical knowledge and seldom questions its validity. Moreover, not infrequently he is not even aware of the philosophical basis which provides, as it were, the methodological framework for his research. The problems he is concerned with cannot be qualified either as purely philosophical or as specifically scientific. The solution of his problems calls for bridging the gap between philosophical and specialized knowledge so as to permit philosophical ideas to fertilize his practical work and give it a new meaning and new dimensions. Such problems can be called philosophico-methodological since they are philosophically oriented and their solution is guided by general philosophical principles. Yet they are not regarded as philosophical, since their emergence does not cast doubt on the content of philosophical categories, nor does it question the role of philosophical laws. It is not surprising therefore that a scientist may delude himself into thinking that he is completely free of any philosophical propositions or principles. It should be noted that empirical investigations in one or another specific field are not likely to add much to the arguments for or against some philosophical trend, even if the facts the scientist deals with are quite extraordinary. Numerous evidences regarding flying saucers and the abundance of documentary reports about catastrophes in the area of the Bermuda Triangle give rather impressive data and stir up imagination. On the basis of such information a layman may come to most fantastic conclusions. Generally speaking, the thinking of a man in the street is apt to overcome very easily the compatibility barriers which often make a tremendous problem for a serious scientist. A layman's imagination can easily carry him from the rumors of flying saucers to a very plausible image of a visitor from outer space described sometimes in great detail, and further to fantastic pictures of the arrival of reasonable beings on the earth. Then he may plunge into speculations on the nature of reason, on the origin of the solar system, etc. Strange as it may seem, what is easily accessible to the layman's fanciful imagination proves to be beyond the power of thinking of a scientist who cannot resort either to Pegasus wings or to Hermes sandals, but has to follow his thorny path with the heavy tread of an experimentalist. His every step must be thought out and well measured. To be sure, science has also learned to build castles in the air now called orbital stations. Yet how very careful and arduous its every step forward, how modest its achievements in comparison with the ages of hard work and relentless struggle against the unknown and therefore terrifying forces of nature, and how very different the sober and restrained approach of true scientists from the unfounded conceit of dilettantes relishing man's would-be power over nature. Alas, the position of an empirically minded natural scientist differs but little from the thinking of a dilettante venturing to expound his views on the philosophical doctrines he knows only by hearsay. He is doomed to vacillate from the extreme exaggeration of the significance of his own achievements and the derogation of the role of theory, particularly philosophy, to the concoction of astounding theories and original philosophical doctrines. It is the empiricist style of scientific thinking and investigation, the empiricist standard of scientific progress, that lies at the root of metaphysical ideas and speculative propositions which fill in the gaps between individual isolated facts torn out of the context and viewed outside and independent of their links and relationships. It is narrow empiricism in science that often takes a disdainful and intransigent stand against consistent materialist approach to reality, and tends to replace serious scientific investigation by pretentious, extravagant ideas without bothering to trace them to the corresponding historical or historical scientific antecedents in the age-old history of science and philosophy. This unwillingness to study philosophical traditions and historical links accounts, above all, for uncritical attitude toward general theoretical and philosophical ideas which are unavoidable in any scientific investigation. Every researcher seeks to transgress the bounds of his immediate investigation and take a broader view of the problem he is concerned with. Yet such transgressions need not necessarily testify to the expansion of his scientific horizons and broadening of his interests. They may also result from scientific adventurism, which goes hand in hand with the condemnation of primitive materialism, theoretical dogmatism, etc. This militant empiricism, which has always chafed under the so-called harshness of dialectics and complained about the pedestrian style of Marx's thinking and the intransigence of Leninist materialism, proves to be capable of getting on quite well with those theories and philosophical concepts which suit it in one way or another in a given situation, gratify its weaknesses. This attitude is usually expressed in overall hostility to any methodology, in anarchical opposition to any world outlook, and results from the absence of a solid theoretical foundation. The uncritical attitude to the philosophical environment leads to a paradoxical situation: on the one hand, ostensible independence, the absence of any philosophical commitments and freedom to choose any philosophical concept that is suitable from the practical, utilitarian viewpoint and justifies all sorts of wild digressions into the history of science or depth of the universe. On the other hand, actual bondage to current philosophical tastes and intellectual fashion. The illusion of freedom from philosophical systems turns out to be overall dependence on obsolete philosophical theories. The champions of the freedom of intellect find themselves in the position of those natural scientists who were so aptly ridiculed by Engels. Natural scientists believe that they free themselves from philosophy by ignoring it or abusing it. They cannot, however, make any headway without thought, and for thought they need thought determinations. But they take these categories unreflectingly from the common consciousness of so-called educated persons, which is dominated by the relics of long obsolete philosophies, or from the little bit of philosophy compulsorily listened to at the university, or from uncritical and unsystematic reading of philosophical writings of all kinds. Hence they are no less in bondage to philosophy, but unfortunately in most cases to the worst philosophy, and those who abuse philosophy most are slaves to precisely the worst vulgarist relics of the worst philosophies. Among such slaves found itself not only positivism, but also other philosophical schools which undertook to express the empiricist's curtailed worldview and carried to excess all the demerits of empirical investigation. The empiricist's stand is in fact hypocritical in that his abuse of philosophy and metaphysics often serves as a smokescreen for his own philosophical system intended to espouse his views. It would be wrong to think that the tendency to exaggerate the role of sensory experience characteristic of earlier empirical science will die away by itself in the age of the maturity of science with its high level of abstractions and complex mathematical formalization of whole branches. The empirical investigation of individual objects and phenomena will always remain an important task of science, however attractive and promising theoretical research may be. It is essential, therefore, that alongside the encouragement of young scientists in fundamental investigations due attention be paid to experimental work and that appropriate incentives be constantly sought to improve and stimulate it. Sometimes an individual fact discovered by mere chance may lead to the emergence of a new scientific trend or to the reappraisal of current scientific theories. On the other hand, as long as scientific investigations in certain fields are based on empirical data, there exists a nutrient medium for empiricism as a philosophical trend. There is yet another paradoxical aspect of the evolution of positivism. The dominance of empirical methods in natural science and the universal enthusiasm about its achievements had come to an end or at least considerably subsided by the mid-19th century. At the turn of the 20th century, the prestige of empiricism was completely undermined by the rapid development of physics, chemistry, biology, and psychology. Yet it is precisely this period that reanimated the influence of positivist philosophy. The development of theoretical natural science and elaboration of fundamental theories did not change the attitude of positivism to general philosophical problems. Logical positivism that came to the foreground in that period with renewed determination to eliminate metaphysics from science was nurtured by the hopes that all theoretical propositions could be reduced to empirical knowledge. This stand was well illustrated by Russell's attitude to the principle of causality in scientific cognition. Characterizing this principle as purely metaphysical, as a relic of the pre-scientific stage of knowledge, he pointed out that theoretically developed sciences had already got rid of all remnants of causality. Alongside the principle of causality, positivism threw overboard all other philosophical principles and laws, first and foremost those of dialectics and materialism, on the grounds that the categories of quality, matter, necessity, essence, and the like are alien to theoretical knowledge. Modern philosophers of science in their works devoted to the concept of law and to the principle of determinism in fact identify law with universal assertions on the grounds that the language of science does not express any necessity except the logical one. Necessity itself is identified with universality which, in their opinion, is all that is demanded of scientific statements, theoretical generalizations, and even the most advanced modern theories. Similar is their attitude to the categories of contradiction, essence, and practically all other main categories and laws of dialectics. Such oversimplified understanding of the structure of scientific knowledge revealing itself in present-day positivist literature is a natural consequence of the main premises of the philosophy of science limiting the philosophy and methodology of science exclusively to the logic and language of scientific cognition. Regarding the available knowledge as reality itself embodied in language, the positivists cannot but overlook the infrastructure of science, i.e. its abstractions, premises, and assumptions. True, the latest variants of positivist philosophy, e.g. critical rationalism and other post-positivist trends, go as far as recognizing the methodological, instrumental role of some principles of dialectics, such as causality and determinism. Yet they also stop short of recognizing the theoretical significance of philosophical categories and laws, pointing out that they do not reveal themselves openly either in theoretical or in empirical knowledge. The view that philosophical substratum does not lie on the surface of scientific theories and empirical investigations is on the whole not objectionable. The question, however, consists in whether the principles and laws of dialectics are indeed devoid of any scientific significance and play no part in theoretical investigations. To answer this question, it is necessary first of all to take into account some specific features of theoretical knowledge. Understandably, the formulation of philosophical propositions and principles goes beyond the limits of a special scientific investigation. Philosophical principles seldom come to the forefront in a scientific system, and their cognitive value is seldom conspicuous. As long as any philosophical principle or, for that matter, any theoretical premise in general serves the purposes of scientific investigation, the scientist is not confronted with the task of its further elaboration or improvement. And it is quite natural. His immediate aim is to solve a specific problem within a more or less narrow field of his interests. He achieves this aim directly, using the means of his particular science: physics, chemistry, biology, psychology, etc. Philosophical principles for the scientist are something like air which he does not think of as long as his breathing is not difficult. What is more, this approach is evidently suggested by the very object under investigation, since it appears to be the most promising and likely to yield the best results. As a matter of fact, the object of investigation often proves, so to speak, more dialectical and more materialistic than the theoretical views of the investigator himself, particularly if his philosophical baggage consists of meager positivist abstractions. In any case, the scientist does not pose any philosophical problems in his field of investigations as long as the concepts he relies upon in his practical work perform the function of the foundation of science. The theoretical significance of philosophical principles and laws would, perhaps, never come to light if they always remained but implicit. Yet sooner or later the time comes when philosophical concepts do reveal themselves to celebrate their victory and claim universal recognition. Unlike experimental data and theoretical principles which lie at the root of specific theories, philosophical principles and laws should be regarded as their premises, since it is impossible to deduce from them any particular scientific doctrine. At the same time, no scientific theory is conceivable without the corresponding philosophical basis. Hence, philosophical premises are essential, but not sufficient conditions for theoretical and empirical cognition. As distinct from theoretical concepts which serve as a basis for a nascent theory so that it is largely deducible from them, philosophical concepts constituting its foundation cannot be used for deducing one or another variant of this theory. As a matter of fact, there may be several ways of solving a problem which would meet the requirements of materialism and dialectics, i.e. scientific philosophy, under given conditions. Speaking, for instance, of the philosophical foundation of classical physics, we can single out at least 4 philosophical ideas deeply rooted in all the theories of 19th-century natural scientists. They are, the idea of materiality of the world, the identity of matter and substance, impenetrability of matter, etc., the idea of the absoluteness of space and time regarded as receptacles of matter and as having properties not connected with one another and independent of the movement of material bodies, the idea of absolute determinateness of all changes and events in nature owing to universal interaction governed by the dynamic laws of mechanics and expressed in the concept of Laplacian determinism, the idea of the independence of the object from the subject of investigation, i.e. the concept of the objectivity of knowledge. Since these ideas were linked with the theoretical foundation of contemporary science, they assumed even more concrete forms. For instance, materiality was identified with several material properties such as constant mass, atomic structure, impenetrability, etc. Space was assumed to be filled up with hypothetical material medium called ether, interaction was believed to spread instantaneously, matter and motion were regarded to be indestructible. The existing philosophical premises allowed of several alternative solutions to theoretical problems, making equally plausible the corpuscular and the wave theories, the theory of ether and the theory denying the existence of any mechanical elastic medium, Laplacian determinism and statistical physics, etc. Metaphysical materialism with its one-sided mechanistic conceptions of motion and matter brought natural science to a crisis which was not confined to just one or several fields but affected the very foundation of science, its instinctively materialistic worldview. Radium, the great revolutionary, according to Henry Poincaré, cast doubt on the law of conservation of energy and, consequently, on the idea of the indestructibility of matter. The electron shook the concepts of the indivisibility of atoms and the immutability of the mass of a body, thus undermining the idea of materiality. Albert Michelson's experiments called in question the existence of ether and absolute space, in which the velocity of light should have been higher in the direction of the movement of the source of light, but proved to be variable and independent of the speed of the source of light. In 1901, Peter Lebedev's experiments revealed the pressure of light. The discovery of X-rays in 1895, followed by the discovery of the electron as the atom's main component and of radioactivity, refuted the idea of the indivisibility of atoms. Other philosophical foundations of classical physics were undermined too, the concept of the immutability of nature's primary substances and attributes, of the universality and absolute identity of the operation of mechanical laws both on the infinite and infinitesimal scales. It became obvious that the philosophical doctrines inherited from the mechanistic materialism of the 17th to 18th centuries could not provide a reliable theoretical foundation for the solution of the pressing problems of physics and natural science in general. The essence of the crisis in modern physics, wrote Lenin, consists in the breakdown of the old laws and basic principles, in the rejection of an objective reality existing outside the mind, that is, in the replacement of materialism by idealism and agnosticism. Matter has disappeared. One may thus express the fundamental and characteristic difficulty in relation to many particular questions which has created this crisis. Turning to the philosophical premises of 19th century physics, the physicists unfamiliar with dialectics could not but identify metaphysical materialism with materialism in general. We need not enlarge on this subject, as it has received extensive coverage in relevant Marxist literature and is not, in fact, directly connected with the main point we want to make here, namely, that the philosophical premises of science have no independent significance as long as they do not come in a more or less sharp conflict with the results of scientific investigations and the latest theoretical views. However, an impending crisis in science causes scientists to start revising its theoretical and experimental principles. Yet a crisis may sometimes go deeper and involve also the philosophical foundation of science if it fails to meet the latest requirements. Hence, crises in the development of science can only be avoided if scientists are fully aware of the philosophical principles which underlie the fundamental theories in their fields of investigation. Of special importance here is not only a profound theoretical background of scientific personnel and a thorough knowledge of the history of science, but also sufficient philosophical culture and good acquaintance with the historical sources of philosophical problems. Most serious attitude to the philosophical foundation of a given science is extremely important. It is no secret that the philosophical principles of modern physics were formulated in a general form by Marx and Engels way back in the middle of the 19th century. The definition of matter as a philosophical category denoting the objective reality which exists independently of consciousness provided the necessary guideline for scientific investigations in the late 19th and the early 20th centuries. Progress in physics could only be attained if the electron was regarded not as a purely theoretical construct, not as an object with free will, but as a component part of the atom with a complex structure of its own. The dialectical solution of the problem of the relationship between necessity and chance constituting a single whole laid or was to lay the foundation for the probability approach to the interpretation of quantum mechanical processes, for the correct understanding of probability and the relationship between indeterminacies, i.e. the discoveries made in the first half of the 20th century. The concept of the unity of space, time, and motion advanced by Marx and Engels also gave a clue to the special and general theories of relativity. It stands to reason that the implementation of these philosophical concepts required of natural scientists conscious assimilation and further development of the philosophical ideas of Marx and Engels, providing a theoretical basis for dialectical interpretation of concrete physical, biological, chemical, and other data. Of great importance for the accomplishment of this task was close cooperation between philosophers and natural scientists. However, conditions at that time were not yet ripe for such cooperation. Even this short historical survey shows that philosophical knowledge is not doomed to remain forever behind the scenes. Sooner or later it is bound to come to the forefront of scientific progress. An essential distinction of fundamental theoretical investigations from empirical cognition consists in that theory is capable of setting and solving a number of philosophical tasks on its own. This feature, naturally, is largely accountable for the difference in the attitude of scientists representing the two tendencies in the development of science to the significance and value of philosophical problems and to philosophy in general. The task of fundamental investigations consists in explaining the established laws, revealing the links between them, predicting and foreseeing new facts and new trends in the development of science. Theoretical laws and concepts therefore express necessity and are of a general nature. Theory no less than empirical sciences rests on a philosophical basis in the form of adopted and tested philosophical doctrines and principles, instrumental methodologically in the formulation and explanation of new laws and relationships. Hence, theoretical investigations also involve problems which we call philosophico-methodological and which are mainly connected with the use of the available philosophical propositions, principles and laws in the solution of methodological problems and in the fulfillment of concrete theoretical tasks. To be sure, the philosophico-methodological approach to the problems dealt with in a theoretical investigation is essentially different from the approach to the same problems in an empirical investigation aimed at revealing and explaining individual facts of scientific importance. For instance, the problem of the objectivity of knowledge viewed from the philosophico-methodological angle at the theoretical level of cognition may boil down to deciding on whether the theoretical analysis of a quantum mechanical ensemble should be carried out with the help of a certain apparatus or whether a basically new means of investigation should be sought in order to make the process under observation independent of the observer. Of course, the effect of an apparatus on the micro-object is an objective phenomenon, but the nature of the apparatus and the form of its influence cannot but tell, in one way or another, on the subjective perception of the processes in interest. It would be wrong, therefore, to deny the fact that object-subject problems do arise in such investigations. Moreover, it can be asserted that no effective solution has been found to this problem so far. The problem of causality regarded from the philosophico-methodological viewpoint at the level of theoretical cognition may consist, for instance, in the theoretical explanation of discovered laws, in the logical deduction of a certain proposition from several premises, in the forecasting scientific and technological progress, etc. Here, too, the content of the principle of causality, the meaning of the categories are not subject to any special analysis. Hence, the problems which we call philosophico-methodological have to be solved both by a theorist and an empirical scientist. Just like in the case of empirical investigations, they are not regarded as philosophical problems mainly due to the fact that the solutions sought are expected to help in the fulfillment of a specific scientific task rather than in the formulation of a philosophical conclusion. The solution of the specific problem in question is subordinated to the principal aim, the solution of a definite puzzle, a special theoretical problem. Similarly to empirical knowledge, theoretical knowledge also has its limits. A theorist takes over where the empiricist leaves off. He formulates empirical laws, explains them, links to other laws having the same degree of universality or to even more general laws, gives them a theoretical substantiation. Scientific conclusions have different degrees of universality expressing the necessary links and relationships at different levels of generalization. Some theories, e.g. the lever theory, differ but little from empirical generalizations as they describe the properties of concrete objects and phenomena. Other theories, such as the general systems theory, the set theory, the games theory, the modern cosmological theories, and others come very close to philosophical concepts and conclusions. As is known, a scientific principle can only be refuted by another one if they represent similar or at least comparable degrees of generalization. Consequently, critical attitude to existing philosophical concepts, as well as real interest in the development of philosophical knowledge, which is indicative of the growing understanding of its role and significance in modern science, can only appear at the theoretical level of scientific cognition. It does not mean, of course, that the responsibility for developing philosophical knowledge rests exclusively with the natural scientists. The point is that the revision of philosophical principles, however partial, calls for their reassessment and creative development, since the problem is not confined to the concrete expression or application of current philosophical laws. It is laws themselves, their content, that become the object of scrutiny. The problems which arise in such situations can be called theoretico-philosophical or worldview problems. The very nature of these problems makes it impossible for the natural scientists to tackle them on their own, though their solution may predetermine the results of investigations in the specific fields they are concerned with. The professional philosophers, for their part, need profound theoretical knowledge in highly specialized fields of positive science in order to undertake this task. They must have a clear understanding of the conflicting theoretical views in the given branch, know its history and traditions. History knows many examples when the natural scientists set themselves the task of solving philosophico-theoretical problems arising in their fields in order to help overcome the crisis. Among prominent natural scientists who made invaluable contribution to the theory and philosophy of science are such famous names as Albert Einstein, Wolfgang Pauli, Niels Bohr, Werner Heisenberg, Vladimir Bekhterev, Ivan Pavlov, Nikolai Vavilov, Ernst Bauer, Vladimir Fock, Dmitry Blokhintsev, and others. In this context, utterly absurd appear to be the repealed attempts of the positivists to lay the blame for unsolved philosophico-theoretical problems and deadlocks in science on none other than philosophy, Marxist philosophy in the first place. Positivism has always been trying to make Marxist philosophy the scapegoat for the difficulties encountered in the process of scientific cognition. Be it the comprehension of the philosophical problems of the theory of relativity or the painful process of consolidation of the quantum theory, the guilt for the protracted debates and controversies was invariably laid at the door of materialist dialectics and the Marxist philosophers who were allegedly opposed to the adoption of new ideas in physics. The development of genetics, too, purports to have been hampered by ill-intentioned dialectics which, according to the positivist historians of science, did not serve as a guide for scientific thought but acted as a brake on its progress. The history of science shows that theoretico-philosophical problems emerge as an expression of contradictions between the available theoretical basis of science and its philosophical foundation. Philosophical arguments are only resorted to when a theoretical problem cannot be solved by purely theoretical means and when it becomes necessary, on the one hand, to analyze its scientific roots and, on the other, to formulate its essence in philosophical terms and to indicate the possible ways for its solution. This, in turn, calls for a sufficiently high philosophical culture. The history of science knows a great many examples when the natural scientists proved incapable of solving important philosophical problems only because they allowed themselves to be enslaved by obsolete or basically false philosophical doctrines. On the other hand, cases are on record when even prominent philosophers adhering to an advanced philosophical teaching were unable to understand the significance of pressing theoretico-philosophical problems as they lack sufficient scientific background or specific knowledge in the particular field of science. Neither physics, biology, nor any other special science can be blamed for the inability of individual scientists to provide correct answers to topical problems of worldview significance. Physics cannot be held responsible for the inability of such scientists as Mach and Poincaré to interpret materialistically the results of their own scientific investigations. Similarly, it is not the fault of Marxist philosophy that some of its ill-starred representatives abused and denounced cybernetics as a bourgeois pseudoscience because they were unable to distinguish between its real scientific content and the misrepresentation of its discoveries in Western philosophical literature. Hence, neither side alone can be held responsible for inability to understand and overcome one or another crisis in the theoretico-philosophical field. The fault lies both with natural scientists and philosophers. Once physicists misjudge a certain discovery, their error is seized upon by philosophers and becomes a source of groundless philosophical illusions and absolutizations leading, as a rule, to idealism and priestcraft. Should a slip be made by philosophers, their delusion will immediately tell on the relations between the rival schools in the corresponding field of positive science. Any controversy over methodological or philosophico-theoretical problems is equally sensitive to both philosophical and specifically scientific arguments. Of course, it always takes scientists some time to realize that they are faced with a theoretico-philosophical problem. If any symptom of an impending crisis in science becomes evident, philosophical concepts and principles are always the last to be called in question. A wrong prediction or explanation in some specific field of science leads first of all to the revision of theoretical principles and corresponding scientific theories. Such a revision takes several years of scrupulous and wearisome work even in our age of the scientific and technological revolution. The turn of the philosophical concepts constituting the foundation of a given theory comes only after scientists complete a most exacting test of the empirical basis and axiomatic premises of the theory in question. There are many hot areas in modern science where philosophical concepts and ideas are tested for strength by new scientific discoveries. As in Engels's time, nature remains the touchstone of dialectics and gives ever new evidence that it is governed by the laws of dialectics, and not metaphysics. The intensive development of modern science, characterized by the ever-increasing complexity of its structure and growing sophistication of its theoretical framework, expands further the sphere of man's knowledge. Scientific investigations extend to ever new fields, new objects, phenomena, and properties of the material world. This statement may seem quite trivial, yet it is not always realized that the expansion of scientific horizons is a transgression not only of the bounds of available knowledge, but also of the bounds of the current theories and adopted paradigms. This latter circumstance is of special significance since the current view tending towards some kind of pantheism maintains that practically all new facts discovered by modern science do not go outside the framework of commonly professed theories, at least the fundamental ones, such as the theory of relativity, the quantum theory, the theory of the atomic structure of matter, and the Darwin theory. True, so far as the modern means of scientific investigation are concerned, there are no grounds to question the validity of at least one of the above fundamental theories both in the macro and micro worlds. Nonetheless, it is rather a weak argument in favor of pantheism. First of all, science has already received certain empirical data and theoretical conclusions which are not quite compatible with current theories, even with such a comprehensive one as the general theory of relativity. The explanation of these facts calls for a special scientific investigation. It is quite likely that a more thorough analysis will bring these facts in full conformity with the theory in question. Yet a possibility cannot be excluded altogether that it will have to be modified, generalized, or even replaced by a basically new theory. Besides, it is never to be forgotten that all current theories, however broad they may be, cannot claim to account for all the properties and aspects of the objective world. In other words, science can still reveal vast areas, explored but partially or unexplored at all, even in those fields where one or another fundamental theory appears to be indisputable. Take, for instance, the complex ecological processes or meteorological phenomena we are still trying to find a clue to and sometimes get the badly needed answers when they are already useless. The Earth's bowels, too, are full of mysteries, not to speak of our nearest neighbors, the Moon and Mars, which are to be explored in the near future. Here we have no proven theoretical concepts whatsoever to rely upon. One can hardly expect to get the right perspective of the relationship between philosophy and science if he ignores the present trends of scientific development, however inconspicuous and insignificant they may seem. One should take into account the fact that the relations between philosophy and some natural sciences or their departments concerned with these latest trends tend to become ever more direct and unmediated. The point is that, in the absence of a developed theory providing a direct and specific explanation of a given phenomenon and predicting its consequences, the functions of such a theory largely pass to general philosophical concepts and principles. To be sure, an essential role in the development of specific scientific theories giving an exhaustive and concrete interpretation of facts belongs also to theoretical or general scientific categories and principles. Yet philosophy plays an independent theoretical part, too, and advances problems which may be called philosophico-theoretical. What are, for instance, those basic scientific principles which constitute now the theoretical core of ecological knowledge, the embryo of the future special theory? They are nothing but a set of philosophical categories concretized to meet specific conditions. In geography, these basic categories represent the concepts of structure, dynamics, development, and others. Thus, the landscape axiom is formulated as follows: in each point of the Earth's surface individual elements, components, and factors of geographic substance are interconnected within a system of diverse and law-regulated orderly ties. The chorological axiom postulating spatial interdependence reads thus: all geographical phenomena are related to some geographical places which are identified by their location and particularly by the connection of this location with neighboring places and areas. Here is the distinguishing feature of geographical objects. In geographic reality there are no objects which do not possess such geographical properties as location and spatial ties. As one can see, all these initial theoretical propositions are essentially concretist basic methodological and worldview principles. Alongside the worldview and methodological functions, dialectico-materialist philosophy performs an important theoretical role. Such an understanding of the functions of philosophical knowledge may at first seem to be a revival of the concept of natural philosophy discarded by Marxism way back in the 19th century. Yet the emphasis on the theoretical significance of philosophy has nothing in common with old natural philosophy, if only for the fact that materialist dialectics, providing the initial theoretical basis for natural science, does not by any means claim to substitute philosophical principles and speculative hypotheses for the subsequent detailed investigation of the object and for the specific laws governing its functioning and development. The absolutization of philosophical knowledge, the speculativeness characteristic of the natural philosophy of the 17th and 18th centuries, are ruled out by dialectical materialist methodology itself. Marxist-Leninist philosophy points the way for science to a more profound knowledge of the world, stressing the need to pass from general philosophical principles to concrete objects, and proves the necessity of discovering ever new aspects and empirical laws of reality. According to dialectical materialism, philosophy should not keep aloof from this process, letting science stew in its own juice and expecting it to ripen all by itself, evolve true philosophical principles, or provide yet another proof of dialectics. Bad natural philosophy cannot spring from the methodology of dialectical materialism. It flourishes where the theoretical progress of science is made contingent on pseudo-philosophical generalizations and ontological interpretations of physical, chemical, biological, and other specific data. Such generalizations and interpretations, claiming the role of philosophical categories, actually tend to replace true philosophical knowledge by speculative, natural philosophical concepts. It would be a mistake to presume that the appearance of natural philosophical concepts can be effectively prevented in our time by the spontaneous development of science and by Marxist criticism. That is not so. When propounding the Marxist-Leninist understanding of philosophy, it is necessary to analyze not only the positivist views, but also the natural philosophical concepts, e.g. within the framework of so-called scientific realism, even if they spring up from a seemingly materialistic soil. This circumstance deserves special attention, since the present crisis of positivist philosophy tends to stimulate the revival of metaphysics as one of the alternatives to the positivist methodological program. It is precisely this alternative offered by Western specialists in the methodology of science that leads to the reanimation of natural philosophy in its modern form. Numerous publications by American and British authors confirm it with utmost clarity. It has already been pointed out in philosophical literature that the mere process of the generalization of scientific data resulting in the creation of universal theories and concepts does not yet produce any increment in philosophical knowledge. In point of fact, such an increment gives grounds for various speculative, scholastic concepts and hypotheses. This approach is untenable for several reasons. First, the conclusions based on the simple generalization of concrete scientific data cannot but be trivial, as they do not solve any real philosophical or special scientific problems. In fact, Any generalization can only be regarded as scientifically valid if it ensues from the solution of a real philosophical problem. Hence, to qualify as philosophical categories or principles, any notions and generalizations should be interpreted in the light of the basic principles of dialectical materialism, tested for relevance and consistence with other philosophical categories and laws. Second, such conclusions are scientifically barren as they do not lead to any new problems. Third, such conclusions tend to distort the philosophical picture of reality, and this is perhaps the most serious defect of the method under consideration. Not a single notion can gain circulation and be used in a philosophical context, in debates or discussions, unless it is assessed from the viewpoint of the main question of philosophy. Why is it so important? First and foremost, because philosophical analysis is based, at least in relation to the worldview and methodology, on the already existing concepts and theories which, understandably, possess both the objective content and subjective elements. One should clearly understand the dialectics of these two aspects of scientific knowledge and distinguish one from the other in order to avoid errors in manipulating the new notion and trying to solve philosophical problems. Suppose, we discuss the cause-effect problem in the light of the feedback concept. Its solution can only be obtained if we present the above categories as abstractions. For a physicist, biologist, a specialist in cybernetics or, for that matter, in any other field of natural science, this problem simply does not exist. Specialists do not deal with the categories of causality and feedback, but with objective processes themselves. In this context, the above categories are not regarded as abstractions with corresponding approximations, assumptions, etc. In objective reality, feedback links are inseparable from causal links. Besides, analyzing the processes of control in terms of feedback relations, a scientist practically does not resort to the concept of causality. It means that these concepts have quite definite epistemological limits which also determine the sphere of their application. Hence, the applicability of one or another concept, and we are speaking here about scientific concepts of a very general nature, depends not only on the specific field of objective reality, but also on the epistemological bounds. The transgression of such bounds, as well as the use of theoretical categories in an alien field, renders them nonsensical. The solution of one or another question from the philosophical angle requires special attention to the epistemological bounds of notions and concepts. In this respect, the philosophical approach, making a sharp distinction between the objective and subjective aspects of scientific facts and ideas, is essentially different from the approach of the natural scientists, just like philosophy in general is different from the knowledge accumulated in physics, biology, chemistry, and other particular sciences. Of course, the basic question of philosophy is not the only filter for scientific generalizations which are to qualify as truly philosophical categories of worldview significance. No less important in this respect are the fundamental laws and categories of materialistic dialectics. It should never be forgotten that the transition from the special knowledge obtained within the framework of some positive science to the philosophical level of thinking, like the process of scientific cognition in general, has very little in common with a linear and unidimensional process of successive generalizations, something in the nature of epigenesis. This transition is a qualitative change, a swing to a different level of universality and, accordingly, to a different level of comprehension of the necessary links and relations of the objective world. 5. Dialectics and the Integration of Science. By Igor Naletov. The contemporary development of scientific knowledge is characterized by certain peculiar trends very important for understanding the relationship between philosophy and science. These trends testify to the fact that dialectics is a replica of objective reality and therefore provides the best method for its cognition. For one, dialectics highlights the objective character of such a profound intrinsic contradiction of scientific and technical progress as the unity of integration and differentiation of science. These two processes account to a considerable extent for the growing complexity of the structure of scientific knowledge and cannot but affect the progress of philosophy itself. Their objective and veracious presentation and assessment can only be undertaken by a philosophy which is fully cognizant of its own dependence on the general trend of scientific development, yet is not susceptible to particular influences within each special science. It is only this kind of philosophy that is capable of viewing the development of science from the inside by virtue of its being its integral part and, as it were, its spokesman, and from the outside, as the exponent of its most general laws, principles, and categories. From the viewpoint of dialectical materialism, which is the only philosophy capable of the above approach, the main and most essential trend in the development of modern science consists in the growing interdependence of natural, social, and technical sciences. This trend does not fall in with either positivist or any of the post-positivist models of the development of science. It is highly significant that this fruitful cooperation is based on modern production and its achievements, on the one hand, and unsolved problems, on the other. Marx's prediction that science will eventually turn into a direct productive force of society is coming true, and this fact is gaining ever wider recognition. Understandably, this applies primarily to natural and technical sciences. Their increasingly close interaction stems not only from the needs of production and from social tasks, but also from the inner logic of scientific development, from the vital tasks of fundamental and applied research. The very links between science and production, the effectiveness of scientific investigations and fundamental research depend to a considerable extent on the depth of integration of scientific knowledge. An important feature of scientific progress in our time, which is overlooked or deliberately ignored by all modern philosophy of science, is the rapidly increasing significance and theoretical independence of social sciences. Their growing prestige is connected with spectacular achievements of Marxist thought in transforming social relations and in the successful management of society in the socialist countries, with the consolidation of the principles of socialist ethics and social humanism. Yet the immediate objective cause of this process is the increasing role of social sciences in the sphere of social production. Under the conditions of modern scientific and technical progress, profound knowledge of the achievements and problems of social sciences becomes a prerequisite for the successful development of natural science and should be regarded as an important element in the general scientific and cultural background of a modern scientist. The role of social sciences should not be confined to giving a specialist in natural or technical sciences a certain minimum of knowledge just to broaden his outlook. They should also provide him with relevant social information to permit solving complex problems he may encounter in his more or less narrow field of activity, let alone the tasks of preparing him for socially useful activity, solving organizational problems, broadening his philosophical horizon and improving ideological education. The very logic of scientific progress, the law of the development of modern science, calls for a broad humanitarian education of the so-called narrow specialists. Under the impact of the current scientific and technological revolution, social sciences, particularly some of their applied disciplines, penetrate into the very core of production processes, revealing new possibilities for the solution of important theoretical and practical problems and for enhancing the efficiency of production. The revolution gives a powerful impetus to the development of new forms of interaction between theoretical and experimental investigations within the framework of natural, social, and technical sciences. The current scientific and technological revolution is connected primarily with the discovery and use of atomic energy for peaceful purposes, with the development of automation and computers, breathtaking achievements of chemistry, rapid progress of biology and space flights. Natural science plays today a crucial role in developing qualitatively new instruments of labor and new materials, in introducing basically new technological systems, designing automatic machine lines, introducing on a wide scale automated control systems, and in solving many other important problems. Tremendous achievements of modern science and technology have made it possible to start fundamental investigations of the structure of matter in micro and macro COSM, to design and develop complex technical systems, investigate and reproduce the most intricate systems of living nature, including the human organism. The current scientific and technological revolution is also characterized by the essential enhancement of the human factor in production, i.e. of the role of man as the subject of the production process, by a radical change in the man-science technology system and by the growing complexity of organization and management. A crucial role in the investigation of all these phenomena belongs to social sciences, whose representatives take an active part in the development of the theoretical principles of scientific control over socio-economic processes, in the study of numerous factors stimulating creative activity, and in improving industrial engineering and production schemes. The influence of social sciences in the sphere of production is constantly growing, and its cooperation with natural and technical sciences is becoming ever closer and more fruitful. The penetration of social sciences into the sphere of production affects not only the systems of control and organization. Changes in the man-science technology complex go side by side with the revolution in the very foundation of production processes. The growing complexity of the design and operation of modern machines, their increasing role in the automation and management of production make ever more exacting demands not only on natural, but also on social sciences, which have to supply the necessary data for engineering solutions. The present level of integration of social, natural, and technical sciences makes it incumbent on engineers, designers and specialists in cybernetics to take accurate account of social, psychological, and other human factors in production, in the service industry and in other fields. The development of new technology and the extensive use of automation, data processing equipment, and computers are primarily the result of the labor of mathematicians and specialists in cybernetics and electronics, yet the achievements in these fields are also creditable to the creative endeavor of logicians, linguists, psychologists, specialists in mathematical economy and economic cybernetics. It is common knowledge that computers which are indispensable in modern production systems cannot be constructed and operated without the solution of economic, psychological, logical, and linguistic problems. As a result, new sciences come into being, such as applied linguistics, human engineering, and economic cybernetics. The computerization of industrial processes is impossible without the modeling of numerous thinking operations, so far comparatively simple, and without solving the problems connected with translation from human language into machine language. The highly accurate operation of automatons is known to be controlled by algorithm-based programs representing the models of production and social processes. The creation of artificial languages, the systematization of terms and symbols, the development of modeling systems have expanded the scope of application of linguistics, which was originally confined to the problems of teaching the native or foreign languages and translating from one language into another, and had very little to do with direct production processes. The extreme complexity of systems which include man as their component, calls for new research methods essentially different from the traditional physico-mathematical analysis. Linguistics, for instance, holds out much promise in the field of modeling such systems, as it permits using not only digits, but also words and even whole sentences of the natural language. Profound investigations into the structure of the natural language, the analysis of the laws governing its formation and functioning are also helpful in the solution of certain technical problems, such as the improvement of the quality standards and responsiveness of the press, automation of some editing and publishing processes, etc. The acceleration of scientific and technical progress, the development of effective control systems result in the rapid increase of information flows which have to be processed at an ever-growing rate. The participation of linguists in the improvement of production and social processes with the use of computers finds its expression today in a new linguistic method of investigation, the modeling of the linguistic system and speech processes. The results of this modeling are materialized in special artificial languages and various linguistic algorithms. Particularly accurate should be the modeling of speech processes when developing dialogue-type systems and other advanced methods of man-machine interaction. Applied linguistics is called upon to make its contribution to the essential improvement of all systems using the natural language and to the enhancement of their effectiveness. Specifically, it should enable computers to receive information in its natural forms, without any preliminary preparation by man. Computers should manipulate semantic units instead of textual elements, sharply expand the volume of information required for the automatic solution of intellectual problems, and open up new possibilities for its complex logical processing. To achieve these aims, it is necessary to develop machine languages approximating to the natural one, create identification devices capable of recognizing human voice or its optical images, and improve the general standard of self-control and self-perfection of machines within the man-machine system. The solution of this latter task is now becoming quite feasible owing to the fact that the substance of man's creative activity yields ever more readily to mathematical description. An important role in this process belongs, for one, to human engineering, which describes man's mental characteristics and functions in terms of mathematical language. This can be easily translated into a machine language to fit in human and machine characteristics. A similar function is performed by bionics, particularly psychological bionics. The investigation into the role of the human factor in modern technology throws a new light on such philosophical problems as the man-machine relationship, the specific features of man-machine languages, substantive and formal moments in reproductive and creative thinking, artificial intellect and self-organization, the unity of the algorithmic and heuristic principles of thinking. Social sciences play an increasingly important role in the solution of questions pertaining to the development of a single classification system for various items and terms, to the unification and standardization of documents with a view to producing uniform information for various control systems in production and other fields of social life. In this connection, a need arises to start a more profound investigation into the theoretical problems of terminology, the language of science, and to join the efforts of scientists studying these problems. The creation of such classifiers, as well as the development and introduction of uniform documents, single systems of technical, economic, financial, and other indices should not only reflect the growing information unity of social, natural and technical sciences, but also take into account new trends in the improvement of the organizational structure of the economy, the new level of the development of democratic centralism in the sphere of management and control. Classifiers not only record essential balance links between the economy and control systems, but also serve as the source material for economic and mathematical modeling in all spheres of the national economy. Automation of production and many other problems of social, scientific, and technical progress provide yet another channel for the penetration of social sciences into the sphere of production and for their drawing closer to natural sciences. The more difficult the tasks and the more complex the processes subject to automation, the more imperative the need for studying man and the full diversity of his individual qualities, the social ones inclusive. The focus of attention is shifted on man's activity, and the results achieved in these studies determine to a considerable extent the solution of many crucial problems, both practical and theoretical. From the viewpoint of theory, the investigation of human activity acquires special importance in modeling man's actions and thinking processes. Computers can only simulate the operational and technical functions of human thinking. The procedures characteristic of the actions of machine and man are entirely different, let alone the difference of the mechanisms themselves. The extremely complex nature of human activity cannot be reduced to logico-mathematical algorithms. Attempts at formalizing certain elements of thinking processes, extremely useful as they are, do not yet give grounds for excessive optimism about the possibility of all-round modeling of man's mental activities, developing a full-scale artificial or hybrid intellect, etc. Computers can essentially facilitate, speed up and improve the accuracy of the decision-making process, yet they can also accelerate the implementation of an incorrect decision. The experience gained in the operation of computers has provided convincing evidence that, in contrast to the solution of simple and similar type problems when man's role in automated control systems is limited to setting a task, inserting initial data into the computer and interpreting the formal decision, the attainment of substantive solutions is only possible on the condition that man intervenes in the decision-making process at each stage of the machine operation. It has turned out that the elements of creative approach to the solution of complex problems, particularly in unforeseen circumstances and in cases when logical and mathematical formalization proves difficult, are needed much more often than in the case of simpler problems. Such operations as the identification of new targets in research, the breaking up of the general task into subtasks, the development of new criteria for a new situation, the selection of the classification base and methods of equivalent transformations, and many others include numerous elements which do not yet lend themselves to formal and algorithmic presentation. Therefore, the need for direct interaction between man and machine, i.e. for the man-machine dialogue, becomes more and more imperative. As a result, social and technical sciences find themselves confronted with the extremely interesting problems of the organization and design of human activity in its unity with automation facilities ranging from elementary means to most complex and sophisticated equipment. The difficulties and miscalculations in the development of automatic control systems and automatic devices are not infrequently traceable to the underestimation of the data provided by social sciences. The specificity of economic processes characteristic of a given industry, industrial amalgamation, or enterprise is not always taken into account by automation development engineers, who tend to concentrate on secondary problems, mainly related to accounting, rather than to tackle the key issues of control such as scientific prognostication, scientific and technical progress, etc. New technical means not only make work easier, they change essentially the very nature of labor and shift the emphasis onto man's intellectual abilities by complicating the process of data apprehension and analysis and increasing demands on his ingenuity, creative powers, and ability to make quick decisions in a changing situation. These features of modern production account for the need to extend scientific investigations beyond the traditional field of physical and chemical characteristics of the instruments of labor, quality of materials and energy problems, and to enlist the services of social sciences. Scientific investigations in the field of labor activity should not be confined to technical facilities as such and to man as the subject of production. They should concentrate more and more on the correspondence between man's physical and mental possibilities, aesthetic tastes, and other social qualities, on the one hand, and the properties of modern technical systems, on the other. The problem of man, his concrete role in the transformation of nature and society, is becoming one of the key issues stimulating the most profound integration of social, natural, and technical sciences. Therefore, in considering the task of optimizing human activity as part of the general problem of the rationalization of labor, philosophers jointly with sociologists, psychologists, and engineers ought to think of how to avoid the restriction of man's creative activity by the further automation of production. Non-automated and semi-automated production processes not only limit the worker's freedom of action, but also make it difficult to change from one occupation to another. While projecting new trades and professions in connection with the deepening processes of automation, special measures should be taken to neutralize these negative trends. Seeking to make work easier and more interesting, the development engineers engaged in the rationalization of production processes and technical means and in the improvement of environmental conditions at industrial enterprises are already confronted with the need for designing specific labor operations. These should relate both to individual elements of production, and to technical complexes. The designing of new kinds of labor activity, of more rational forms of interaction between man and nature, man and machine, etc. is still behind practical needs. However, this trend represents yet another important field where natural, social, and technical sciences join their efforts to achieve a common goal. Modern science regards man, machine, and the production environment as a complex dynamic system, with man playing the leading part. A comparatively new branch of science known as ergonomics or human engineering studies the role of human factors in modern production and other spheres of activity and analyzes the integral characteristics of the man-machine system. Investigations in this field cannot be reduced to the analysis of the characteristic features of man, machine, and production environment separately from one another, even if they are viewed in the aggregate. Ergonomics as a science is evidently confronted with the task of developing its own theory and devising its specific methods of investigation into the man-technology production environment system. A comprehensive approach to the problem of man's labor activity based on the achievements of social, natural, and technical sciences throws a new light on many theoretical and practical problems. It makes it possible to correctly assess not only the role of the instruments of labor, technical means, and the real significance of the factors of production environment, but also the place of man in modern social production. Such an important category as the quality of labor, for instance, acquires a new meaning. Economists are at present mainly concerned with such characteristics of labor as its complexity, intensity, physical hardness, importance for society, etc. All these characteristics are taken into account in wage rating practices at state enterprises. However, they cannot reveal in full scope the social effectiveness of labor. The analysis of its quality only from the viewpoint of narrow practical criteria does not fully reflect the specificity of labor under the conditions of developed socialism. Yet the quality of labor is an integral characteristic which represents the product quality and quantity indicators referred to the indicators of man's health and intellectual level. At the present stage of industrial development, it becomes technically possible to realize projects on the basis of a comprehensive approach to man's activity. Under the conventional pattern, design work on a system generally starts from its estimated technical characteristics which determine the place and the functions of the man operator, the latter's role being mainly assessed in terms of limitations. Time has evidently come to reverse this order and try the alternative method. Specifically, in developing a technical assignment, the designers should proceed from the idea of the secondary, auxiliary function of machines and, consequently, take into account, first and foremost, the positive qualities of man as the real subject of labor, i.e. his advantages over the machine, but not his demerits. This approach opens up basically new possibilities for enhancing the efficiency of labor and will eventually make it possible to shift the focus of attention from the solution of the pressing problems of industrial engineering, the improvement of available technical means and the adaptation of man to the existing technological norms onto the design of new forms of human activity based on comprehensive theoretical investigations into man's physical, mental, and intellectual potentialities now being studied by ergonomics. As has been pointed out in the recommendations of the Second International Conference of Scientists and Specialists of CMEA countries and Yugoslavia on ergonomics, the trends in the development of modern production will evidently bring about a situation in which the main design problems will be connected not with the investigation of equipment characteristics, but with the search for ways and means ensuring optimal interaction between man and technical means. The main criteria for such optimization must be the provision of the most rational equipment and the maximum satisfaction of man's need for creative work. Besides the mutual influence of their ideas and methods, the growing interdependence of social, natural, and technical sciences finds its expression in the emergence of new branches of knowledge on the borderlines between them. Ergonomics, engineering aesthetics, applied linguistics, economic cybernetics, etc. can hardly be classified among purely natural or purely social sciences. They do not study man as such or objective relations between people, or the technical aspect of production. The subject matter of these disciplines which constitutes the basis for the synthesis of social and natural sciences is the interaction of man and technical systems, production and natural environments, etc. In this context, special importance attaches to the analysis of complex methodological problems underlying the synthesis of social, natural, and technical knowledge. It is the diversity of possible approaches to man's labor activity in modern production that presents the main difficulty in developing a single language for different specialists concerned with ergonomical problems. Understanding among economists, designers, and psychologists can only be achieved on condition that the synthesis of social and natural sciences is not reduced to a mechanical combination in some aggregate system or conglomeration of knowledge, or even to the establishment of some kind of subordination between them, but is based on the general theory of labor activity. This task deserves most serious attention and calls for extensive investigations into the general principles of human activity. Such investigations should be aimed at revealing the laws governing the perception of data, the shaping of combined pictorial conceptual models, visual thinking, and decision-making processes. Much has already been done in this direction, yet the development of a comprehensive theory of labor activity is still a matter of the future. As a result of the weakness of the general theoretical basis, technical systems are often designed without due regard for the human factor. For instance, man is viewed merely as an auxiliary technical element, and very inconvenient at that, of a control system, and the system is understood as some kind of a computerized complex differing from the conventional one only by the number of technical means employed and by the method of its operation. Such an approach is absolutely untenable from the methodological viewpoint and leads in practice to serious technical and economic miscalculations. Ergonomic investigations are mainly aimed so far at attaining specific aims, rather narrow by nature, the improvement of technical means to meet the requirements of modern production, the optimization of machine tool configurations, the rational arrangement of instruments or control desks and auxiliary equipment, the improvement of controls, etc. True, the scope of these investigations is gradually expanding. Besides the equipment improvement and layout optimization problems, specialists in ergonomics jointly with designers study the possibilities of domesticating the territory of industrial enterprises so that it may merge naturally with the city or suburban complex. They concern themselves more and more often not only with the quality and external appearance of one or another industrial product, but also with the conditions, both natural and social, under which it is to be used. It stands to reason that the scientific solution of the problem of optimal interaction between man and machine in the socialist countries is directed not only towards enhancing the efficiency and economic effect of new technology in connection with the new role of man in the system of modern production. Even a more important aim of this investigation consists in creating the best possible conditions for the development of man and for freeing him from the strain of tedious and monotonous work. The new technology, the extensive use of electronic computers and the overall improvement of production conditions testifies, first and foremost, to the humanitarian mission of science opening up new possibilities for improving man's welfare and ensuring his all-round harmonious development. An important factor in the strengthening of links between social, natural, and technical sciences is the tendency towards the integration of their cognitive potentialities, both theoretical and experimental, as regards the rational use of nature, environmental protection, and the solution of other global problems. The synthesis of social, natural, and technical sciences in the process of the comprehensive solution of various problems leads to the emergence of numerous gravitation centers where specialists in most diverse fields of science join their efforts to achieve a common goal, and accounts for different levels of analysis, including the highest level of the integration of social and natural sciences on the basis of materialist dialectics, which becomes in this case the theoretical and methodological basis for complex scientific investigations. This tendency results in a considerable enhancement of the role of Marxist-Leninist philosophy as the most general theory of the development of nature, society, thinking and the methodology of science. Lenin's idea of the alliance between Marxist philosophers and representatives of special sciences is demonstrating its increasing viability. Under the conditions of socialism, this alliance derives its strength from the principles of dialectical materialism, the objectivity of knowledge, development, causality, existence of objective laws, etc., which provide a solid methodological basis for natural, social, and technical sciences. From its inception, Marxist philosophy has been absorbing the outstanding achievements of natural and social sciences and developing as the methodology of natural knowledge, social knowledge, and the world-transforming revolutionary practice. At the turn of the 20th century, Lenin wrote, "It is common knowledge that a powerful current flowed from natural to social science not only in Petty's time, but in Marx's time as well. And this current remains just as powerful, if not more so, in the 20th century too." The truth of Lenin's words is once again confirmed by the large-scale penetration of the mathematical methods of analysis into social sciences, which use them as an important instrument of sociological, economic, and psychological investigations, and by the application of computers and data processing equipment in the sphere of public opinion studies. The development of science is characterized today by powerful currents of ideas not only from natural to social sciences but also in the opposite direction. The problems, ideas, and methods of social sciences exercise an ever-increasing influence on natural and technical sciences. An important role in their integration belongs to cybernetics, the probability theory, the games theory, and the theory of information. For instance, cybernetics has not only made a valuable contribution to the development of the methodology of some social sciences and to the very style of scientific thinking, but has itself benefited from the alliance with social sciences. As a matter of fact, its very first steps could not but be influenced by such general concepts of progressive social and philosophical thought as target setting, control, systems analysis, etc. The concepts of memory, teaching, game, collective behavior, and others made their way into cybernetics together with the new problems and specific methods of psychology, sociology and linguistics. The investigation into the so-called artificial intellect problems also testifies to the influence of humanitarian sciences on the orientation of cybernetics. The development of data converters and machine programs in line with cybernetic concepts emphasizes the imperative need for studying the nature of man's creative activity and heuristic art and highlights the importance of the knowledge of man and society. The growing interdependence of social, natural, and technical sciences and their methods of investigation, the emergence and rapid development of the marginal branches of knowledge, the tendency towards comprehensive investigations of major economic and fundamental scientific problems by joint efforts of sociologists and natural scientists, all this tends to enhance the role of dialectical materialist methodology. The new conditions causing social, natural, and technical sciences to draw ever closer together pose a number of complex problems of world outlook and methodology before Marxist-Leninist philosophy. Most serious attention, for one, should be given to such problems as the main directions and concrete forms of the integration and differentiation of sciences, the use of methods employed by natural science in sociological investigations, the mathematization of knowledge. The analysis of dialectical transitions between the abstract and the concrete, the general and the particular, the empirical and the theoretical, the substantive and the formal in scientific cognition is a necessary condition for the effective implementation of the ideas of mathematics, mathematical logic and cybernetics in other sciences. Of special importance is the dialectics of the abstract and the concrete, the general and the particular in the analysis of social relations carried out with the use of abstract mathematical and cybernetic notions. In this field the correct subordination of notions, methods, and techniques plays a decisive role. Any formalism and eclectic dovetailing of social, natural, and technical concepts is absolutely inadmissible. All this shows that the increasing differentiation and deepening integration of scientific knowledge pose extremely important tasks before dialectical materialism as the philosophical and methodological foundation of the cooperation of sciences. The philosophic interpretation of the latest achievements of social, natural, and technical sciences is one of the important prerequisites for the further development of scientific world outlook and methodology. Yet the task of philosophy cannot be confined either to the passive registration of these achievements or to their so-called generalization consisting essentially in attaching the tags of philosophical categories to some general concepts worked out by science. The philosophy of dialectical and historical materialism cannot and must not be just a peddler of new ideas and data obtained by other sciences. This philosophy is indeed open for all new and fruitful ideas, yet it does not mean that it is a mere vessel for accumulating general scientific information. Its function is to give a creative interpretation and a dialectical synthesis of new data. This, in turn, presupposes the creative development of Marxist-Leninist philosophy itself, its enrichment with new ideas, the further concretization of its categories representing the sum total of the entire history of man's cognition and transformation of the world. The complexity of integration processes accounts for considerable difficulties in the solution of these problems. The rapprochement and close cooperation of some sciences, such as psychology and physiology, tend to gradually obliterate the borderlines between them and lead some scientists to an erroneous conclusion that their objects coincide. This view is fraught with the danger of overlooking qualitative distinctions between the objects of investigation by these sciences, and this, in turn, may result in the absolutization of certain methods and concepts at the expense of others. In fact, such sciences as psychology and physiology of higher nervous activity study different aspects of the activity of the brain and, consequently, the objects of their interest must not be confused. The psychologist's task evidently consists in studying the socio-historical origin of the most complex forms of consciousness regarded as an independent object of investigation which cannot receive an exhaustive explanation in terms of physiological processes alone, though the latter constitute the basis of the complex forms of man's conscious actions. It is this task which determines the basic methodological principle of the interaction between psychology and physiology. The identification of the subject matters of the physiology of higher nervous activity and psychology bars the way for understanding the socio-historical laws that govern the formation and development of the higher forms of psychic activity and is in fact tantamount to denying psychology as a separate science. Similar difficulties arise in the realization of comprehensive research programs, since their effectiveness largely depends on the assignment of the field of activity for each specialist and on the understanding of his possibilities and advantages in a given investigation. Such synthesis, however, should not be regarded as the simple summation of knowledge obtained by individual sciences. The purpose of a comprehensive analysis is not to obtain data characterizing different aspects of an object and to present them in a summarized form. It consists, first and foremost, in defining the main factor which constitutes the system under investigation and accounts for its specificity and integrity. It is therefore very important to assess correctly the significance of the problems of theory, methodology, and worldview arising in the process of the integration and interaction of individual sciences in a complex investigation. The adequate idea of the basic integrated properties of a complex studied by different sciences can only be provided by a more general theory. Indeed, the experience gained in the development of comprehensive programs of cooperation of natural, technical, and social sciences attests to the fact that such programs, born out of the needs to solve certain practical, applied problems, tend to advance new theoretical questions and actualize philosophical problems pertaining to the activity of man in general, his interaction with machine, the relations between production and the environment, nature and society, etc. Complex methodological problems of the interaction of social, natural, and technical sciences arise not only in connection with the definition of their objects of investigation, but also as a result of the mutual penetration of their concepts and methods. Laying aside the question of the possible forms of such interaction, we shall merely emphasize here that each attempt to apply the methods and concepts of one science in the field of another science should be preceded by a dialectico-materialist analysis of the possibilities of such extrapolation and, consequently, should be viewed as a philosophical problem. Nothing but harm will result from the oversimplified understanding of this process and from the underestimation of those philosophical and methodological principles which underlie the development of social, natural, and technical sciences and their creative possibilities. The uncritical, mechanistic transfer of the concepts and methods of one science, ungrounded extrapolations and formal generalizations can only mislead a scientist. The borrowing of the ideas and methods by one science from another presupposes their creative assimilation and reassessment in accordance with the specific object and tasks of the former. Under such conditions, special importance attaches to the analysis of dialectical transitions from one field of knowledge to another. Any underestimation of the importance of the methodological, philosophical analysis of the borrowed ideas and methods leads either to negativism regarding the possibility of the integration of the methods of social, natural, and technical sciences, or to a kind of euphoria, ungrounded enthusiasm about the cyberneticization, mathematization, formalization, and ecologization of science, often prompted by nothing more than the desire to keep up with vogue. Though the positivist concepts of the relationship between philosophy and special sciences, as well as between social and natural sciences, have gone never to return, the reductionist illusions regarding the relationship between the social and the biological, the social and the psychological, prove to be very tenacious. For instance, striving to trace the roots of crime, some authors are inclined to see them in genetic, i.e. essentially molecular biological mechanisms. Similar tendencies are also in evidence in the interpretation of the so-called biosocial nature of man. This formula looks attractive enough due to its laconicism, yet it tends to oversimplify the mediated relationship between the social and the biological, camouflaging a number of essential intermediate links between them. It is precisely owing to the complexity of this relationship, its mediate character, that social phenomena do not yield either to direct biological explanations or to an interpretation in terms of the so-called parallelism of social and biological factors. To be sure, the dialectico-materialist analysis of high-level psychological processes or social phenomena with all their links and relations of mediation should not ignore the natural determinants of human behavior. Such determinants, however, must be taken into account in unity with all other factors revealing the definitive role of social motives in the activity of man. It stands to reason that the integration and differentiation of science alongside the increasing importance of theory tend to complicate the structure of modern scientific knowledge and its further development. The emergence of such sciences as cybernetics, the games theory, the information theory, and others which study very general laws applicable to entirely different objects and phenomena of reality partly accounts for an illusion that positive sciences no longer need a philosophy and that philosophical knowledge can be at last replaced by general scientific concepts capable of providing the necessary methodological and scientific basis for more concrete sciences. Some contemporary Western philosophers go even as far as asserting that the prophecy of positivism has at last come true and that science assumes the methodological prerogatives which hitherto belonged to philosophy. True, modern science can no longer content itself with the means of the local synthesis of knowledge. A need arises to synthesize the knowledge of interdisciplinary character and to develop additional means for such a synthesis, special integration theories, new branches of knowledge and new scientific trends, such as cybernetics, semiotics, system investigations, a general theory of modeling, a theory of similarity and dimensions, investigation of operations, etc. The additional means for such a synthesis also include new hardware automatic data processors, such as cybernetic modeling machines and computers which essentially enhance the efficiency of brain work by mechanizing and automating mental operations, particularly in the bibliographic information service, which is thus enabled to solve new complex problems. This intellectual industry permits improving the accuracy of weather forecasts, developing many branches of the national economy, accelerating technical progress, etc. Without its aid it would be impossible to carry out extremely complex calculations, exercise control over space flights and solve many other problems. The peculiar position of general scientific disciplines which serve as intermediaries between philosophy and natural sciences results from the two main functions they perform. First, they provide a theoretical and methodological basis for a number of positive sciences. Characteristic in this respect is the connection of these sciences with mathematical methods of investigation which enable them to carry out more general qualitative and quantitative analyses and to apply the general rules of calculation in a given concrete field of investigation. Second, they serve as an intermediate methodological link between certain positive sciences and materialist dialectics as a whole. For instance, the specific methodological function of the theory of similarity which covers physical and physico-chemical processes manifests itself in processing and generalizing experimental data and in modeling physical processes. The conceptual body of the theory of investigation of operations is not limited to mathematics. Its categories and the general principle of investigation provide a particular methodological approach in the investigation of any complex goal-oriented activity, its elements being individual operations. This theory is used in the investigation of many different kinds of human activity, as well as in the analysis of man-machine complexes representing automated control systems. The main principles and categories of cybernetics provide particular methodological guidelines for sciences concerned with living nature and social life, as well as for technical sciences investigating control processes in terms of data processing operations. These include the questions of automatic regulation, self-adjustment, instruction and self-instruction, self-organization, self-reproduction and the development of natural and artificial systems. Hence, from the theoretical and methodological viewpoint integrative sciences provide, as it were, a kind of a bridge to the highest theoretical generalizations and methodological principles, i.e. to philosophy. As we see, the growing complexity of scientific knowledge and the emergence of general theoretical disciplines make the question of the role, of philosophy even more topical. Scientific progress in our time leads not to the withering away of philosophical methodology, but to the further enhancement of its role. The interpenetration of social, natural, and technical sciences and their methods, the appearance and rapid development of boundary scientific disciplines, the trend towards comprehensive scientific investigations of major socio-economic problems which call for joint efforts of social and natural scientists, all these processes attest to the growing significance of philosophical methodology. Such is the viewpoint of materialist dialectics, and such is the trend of scientific development. Within the province of professional philosophers remain, as before, the investigation into general trends in the development of science, the study of interaction between new scientific trends, their relative independence, the applicability of the methods of certain scientific disciplines in the fields of other disciplines, the extrapolation of theoretical concepts to new fields of investigation, reduction problems in their numerous aspects, the unity of scientific knowledge alongside the extreme diversity and dissociation of individual scientific schools, etc., not to speak of the eternal problems arising with new force under the present-day conditions, the objectivity of scientific knowledge, causality, determinism, the dialectics of scientific cognition, and others. The solution of these problems not only calls for excellent knowledge of the latest scientific achievements and of the history of science in general, but also presupposes profound philosophical background and good acquaintance with the history of philosophy. The acquaintance with the basic principles of materialist dialectics is far from sufficient to guarantee success in scientific investigation. No less important is the ability to use them. The successful solution of scientific problems under modern conditions, in the face of highly complex and widely ramified scientific disciplines, depends on the ability to assess available knowledge in the light of general scientific concepts, which is impossible without good knowledge of modern theoretical ideas and the history of science. Philosophical knowledge, owing to its special relations of mediation with concrete empirical and applied scientific investigations, never reveals itself in its pure forms. It is represented in current theoretical ideas and concepts, in the theoretical knowledge related to a given specific field. The influence of philosophy on the character and results of scientific investigation is in fact much more subtle than is purported by some popular scientific and philosophical publications intended to demonstrate with maximum possible clarity the role of methodology and world outlook in scientific knowledge. To be really successful and fruitful, scientific activity must rest on the entire system of dialectical materialist philosophy understood as a single harmonious, integrated world outlook, but not on dissociated scraps of philosophical knowledge, interpreted at that in a very primitive manner. It would be naive to expect that universal theoretical problems can be solved by a specialist in cybernetics, the general systems theory, or by a representative of some other scientific discipline, however broad its field. No less groundless would be a hope that such a task could be successfully accomplished by a philosopher who would be capable of digesting the enormous amount of information obtained by positive sciences. There is no alternative to the alliance between philosophers and representatives of natural and social sciences. The problem, if there is any, can only be over the selection and development of the most effective and adequate form of this alliance. A modern scientist specializing in boundary problems and investigating the crossroads of traditional scientific trends can hardly expect to gain any success in his work even if he is well versed in one of the special fields. It becomes more and more obvious that the more important discoveries in modern science await not a narrow specialist, but a scientist of broad theoretical outlook, a thinker, an intellectual. We may be now returning to the epoch of the encyclopedists, but on a new level of scientific knowledge. At any rate, such a return to the seemingly old appears to us quite possible, and certain symptoms of the advent of a new age of Leonardo da Vinci and French enlighteners are already in evidence. In our time, when much of the tedious work required to accumulate and classify facts can be handed over to machines with their constantly expanding possibilities, the value of experience in some special field of knowledge stands as high as ever. Yet the importance of philosophical, methodological knowledge increases immeasurably, since it is precisely this knowledge that can bridge the age-old gaps between physics and biology, biology and physiology, psychology and mathematics, economy and mathematics, etc. The new disciplines emerging on the borderlines between these sciences are notable for practically direct scientific application of philosophical knowledge. In contrast to 18th-19th century natural philosophy, it plays the role of general theoretical, philosophical principles and concepts and does not claim to provide final solutions to concrete scientific problems. Present-day scientific knowledge is highly dynamic. The current scientific and technological revolution is notable not only for rapid changes in the content of knowledge itself, but also for abrupt shifts in the value approach to different branches of knowledge. It was only quite recently that physics was the idol of the youth. The changing tide then lifted up cybernetics, and the representatives of this promising branch of science enjoyed universal attention. The recent breakthrough in genetics and the acuteness of the ecological problem have sharply increased the prestige of biology. The value and prestige of one or another science and, consequently, its impact on social life and on the style of thinking constantly fluctuate. It is no secret that the current period is marked by a steadily growing interest among the youth in social, humanitarian sciences. Yet it is not only the young that turn up in increasing numbers at these sciences enlistment centers. Far more significant is the fact that humanitarian problems attract more and more full-fledged natural scientists engaged in their specific investigations. Understandably, the natural scientists' attention to humanitarian issues results, first and foremost, from their social, civic interests. A modern scientist cannot conceive of activity removed from social problems and the tasks of scientific, technical, and ethical progress. Under contemporary conditions, philosophy alone can provide scientists with an effective means to cope with the increasing flow of information and expand their theoretical horizon and world outlook. First, it gives them the necessary methodological instruments for safe navigation in the boundless sea of scientific theories and concepts, and guards against unfounded hypotheses and unrestrained imagination. Second, it provides guidelines for the investigation of social problems, giving the necessary information on their character and disclosing the basic principles underlying the development of social, humanitarian knowledge. Such information is essential for scientists in all fields, irrespective of the particular questions they are concerned with. If we view the progress of science from a broad perspective and take full account of the modern tendencies in its development, we cannot but come to the conclusion that success in research and the advance of science as a whole depends as much on the scientist's special knowledge, as on their theoretical background. The latter implies that a scientist should not only be well versed in the adjacent fields directly related to his sphere of interest, but also be familiar with the entire complex of social, natural, and technical sciences. The development of science in the 20th century has convincingly shown that the concepts of the flank and rear in the overall scientific offensive have become completely antiquated, just as the title of the leading science which now reminds one of a challenge prize kept by the winner as long as he is in the heyday of popularity. The prize will inevitably pass on to another science as soon as it draws the public's eye. The concepts of adjacent fields and boundary problems are becoming anachronistic, too. The unidimensional structure of scientific knowledge is giving way to a multidimensional one. Not long ago, physics, or, more accurately, mechanics, was considered to be the only science adjacent to engineering disciplines. Now they have got other neighbors as well, such as engineering psychology, born of the engineering and psychology borderline problems. The study of the architecture of living organisms carried out within the framework of bionics has brought closer together engineering and biological disciplines. Such examples are numerous. The shoots of new scientific knowledge, new scientific trends are appearing and will appear in most unexpected nodal points of this crystal lattice. The boundary problems holding out the greatest promise for scientists should therefore be visualized now in terms of solid rather than plane geometry, i.e. as being disposed in some imaginary multidimensional space where each science can find points of contact with any of its counterparts. 6. Dialectics of the Objective and the Subjective in Scientific Cognition. By Igor Naletov. The above critical analysis of the positivist attitude to the problem of the objectivity of scientific knowledge, as well as the comparison of positivist views with some of the alternative concepts surfacing in the modern philosophy of science, was to highlight, among other things, the inseparable unity of modern materialism and dialectics. One cannot pursue the principle of objectivity of scientific knowledge without concessions to idealism and metaphysics if the materialistic approach is not integrated, merged from the outset with the dialectical methodology of science. It is highly essential that this integration is not a mechanical combination of dialectical and materialistic concepts which supplement one another, but that they are blended in the analysis of the real problems of scientific cognition. The task of blending materialism and dialectics is the more topical at present, as not many investigations can boast integrated dialectical materialist approach to the analysis of concrete scientific problems. Regrettably, the study of special problems is not infrequently guided by the principles of didactics rather than by the dialectics of scientific cognition, and the division of scientific material convenient for its presentation to students often predetermines the principles of scientific analysis. However, methodical schemes invaluable in the classroom sometimes turn out to be too rigid to reveal all the aspects of the interdependence of materialism and dialectics. The importance of this problem is also highlighted by the analysis of the main philosophical trends of our time. As has been shown above, modern bourgeois philosophy reveals an obvious tendency toward materialism. The crisis of the positivist methodology of science gives rise to new philosophical schools, such as critical realism and scientific materialism, which proclaim materialism to be their credo. However, this materialistic trend in Western philosophy does not merge with materialistic dialectics and remains indifferent to its achievements. Moreover, it is often openly biased against dialectics. The fact that many representatives of critical realism recognize the objective reality not only of individual physical objects, but also of general properties and entities, and speak of scientific metaphysics, the development of scientific knowledge, etc., is very indicative of a profound crisis of the positivist philosophy of science. Yet it is but the first stage in the search for new methodological guidelines, since the principles of objectivity and testability of scientific knowledge, correct in general, must be supplemented or, to be more exact, integrated with the dialectical approach to scientific problems. The obvious fact that modern materialism is inconceivable without dialectics is again and again confirmed by concrete investigations. Take, for instance, the old problem of consciousness, whose different aspects are now highly topical. Sociology, pedagogics and social psychology view this problem mainly from the social angle, i.e. in terms of the determining influence of social conditions on the genesis of consciousness. Cybernetics studies the same problem from the viewpoint of the possibility of reproducing the functions of consciousness by cybernetic machines. Psychology and neuropsychology, in terms of the relationship between consciousness and the brain, etc. One can declare himself a convinced materialist professing the primacy of social being in relation to consciousness, indicating that consciousness is a function of the brain, highly organized matter, or pointing out the possibility of modeling the brain processes with the help of computers. Yet none of these statements attests to a consistent materialistic stand unless they represent a dialectical approach to the problem. Once we separate one from the other, which is sometimes the case in scientific publications, we automatically undermine the very foundation of the professed materialistic views. It is common knowledge, for instance, that the content of human consciousness is determined by social factors. One should bear in mind, however, that the prerequisites for the formation of concepts, mental images, reside in neurodynamic processes. Hence, a consistent materialistic analysis of the nature of consciousness is only possible if both sides are taken into account in their interdependence. Should we for a moment lose sight of one of them and rashly state, for instance, that we owe consciousness to social factors only, the ghost of idealism will present itself right here and then. Indeed, since individual knowledge is passed on from generation to generation, our statement would imply the existence of some kind of primordial knowledge which might well assume the form of absolute or innate ideas. Furthermore, this is not the only loophole which would be opened for idealism by our unwary statement. If consciousness is determined by social factors only, how should we account for such phenomena as talent, good inclinations, natural gifts? How should we explain Mozart's musical endowments and Lenin's genius? We should have either to leave these questions unanswered, or appeal for help to providence. In a word, without dialectics we should not make a step toward materialism. Materialism has now reached a stage when its further development as the worldview and as the methodology of scientific knowledge is only possible on the dialectical foundation. Conversely, dialectics cannot be a coherent system of philosophical views unless it rests on the materialistic foundation. The merger of materialism and dialectics is embodied in Marxism-Leninism, which opened a new epoch in the development of philosophy. After the emergence of Marxism-Leninism, any deviation from either dialectics or materialism, any concession to idealism, eclecticism, and metaphysics is bound to undermine the unity of philosophy and should be regarded as essentially regressive. The entire history of materialism shows that it could not be consistent unless it was interpreted dialectically. This was particularly obvious when materialist principles were applied to the explanation of social phenomena. Suffice it to recall Feuerbach. In our time, non-dialectical materialism is simply inconceivable, it cannot but stumble at every step. Modern science and social processes are so complex and dynamic that any inconsistency in world outlook and in the philosophical interpretation of one or another phenomenon is fraught with grave ideological consequences. Each philosophical problem, therefore, should be treated from the viewpoint of dialectical materialism, i.e. from the materialistic and dialectical angles. The materialistic principles themselves will turn into an inadmissible philosophical abstraction if they are divorced from dialectics. In our time, dialectics is opposed not only to metaphysics, but also to idealism. Conversely, materialism claiming consistency is incompatible with metaphysics and all sorts of eclecticism. The positivist concept of objectivity, the Popperian interpretation of objective knowledge, and the stand of scientific realism are notable, first and foremost, for a narrow understanding of the principle of objectivity. Nevertheless, each of the above trends has certain rational elements, and their comparison will help understand more clearly the essence of the problem and define the guidelines for its modern solution. The obvious difficulties encountered by positivism and other trends of the modern philosophy of science in the interpretation of objectivity show that there are but two methodological alternatives open before a philosopher: either to give up the search for objectivity altogether and agree that objective knowledge is unattainable, or to hold on to the materialistic tradition at the risk of earning the reputation of an outdated and even retrograde thinker attempting to draw philosophy back to the ideals of classical natural science. The first alternative appears to be rather attractive. It seemingly complies with the spirit of modern science, which continues blasting one bastion of classical science after another, and relieves the scientists of the need to rack their brains over metaphysical problems, enjoying but little popularity with most of them. At a closer look, however, it does not help to avoid difficulties, since any attempt to carry on investigations with the legalist handicap of the subjective brings the investigator back to the problem of distinguishing between the objective and the subjective, which he tried to escape. This was clearly demonstrated by the fate of the hypothesis of latent parameters in quantum mechanics, which postulated the inevitable presence of the observer in the quantum mechanical theory. As regards the second alternative, i.e. the adherence to the principle of objectivity, it turns out to be a thorny path just as well, and calls for a serious philosophical analysis of the concept of objectivity. What is more, this analysis appears to be the more difficult as it is to provide a basis for mutual understanding between the philosophers and the representatives of special sciences. What was the main weakness in the positivist concept of the objective? In one of the previous sections devoted to this problem, we have shown that positivism identified the objective with the observable. It was through observation and combination of various sensations and perceptions that one could form an intersubjective idea of any object. An individual observation or perception could not, of course, give knowledge independent of the subject, but a series of observations, the perception of recurrent processes were evidently sufficient to provide the necessary material for separating the subjective from the intersubjective. A similar understanding of the objective underlies also the concept of critical rationalism. In his theory, Popper only eliminates the most obvious weaknesses in the positivist interpretation of the objective, but sides with the concept of intersubjectivity. According to Popper, the difference between the objective and the subjective consists only in that the former has passed through the purgatory of intersubjective criticism, which separates the elements of knowledge immune to falsification from those disproved by constantly changing experience. The objective is thus identified with the conventional, the immutable, with what is not questioned by experience at a given moment. The narrowness of such criteria of objectivity reveals itself, in fact, each time science transgresses the bounds of habitual, stereotyped phenomena and events. As regards unobservable processes, relationships and properties, the positivist criterion of objectivity proves to be completely unsatisfactory. Popper's criterion reveals its untenability and inner subjectivism when one fundamental theory gives place to another, since the breakdown of a theory signifies the dissolution of the stable nucleus which cannot be falsified and is, according to Popper, the refuge of objectivity. In its search for objective knowledge, modern philosophy of biology strives to reduce biological knowledge to physical phenomena. Why is it so? Because phenomenalistic theories proceed from the assumption that the stable nucleus of knowledge immune against subjective influence or interpretation can only be defined through the analysis of physical structures on the molecular, atomic, or subatomic levels. This mirage still entices scientists who stake on physicalism and are fascinated by the seemingly clear and tangible outlines of new theories, though this path, as we have shown, is actually a blind alley, and the scientist who takes it in quest of objective knowledge is soon bound to discover it. True, the physicalism of scientific materialism is more constructive, if only for the fact that it is oriented on the recognition of objective reality, creation of scientific ontology and its subsequent verification. In our opinion, it is far less damaging to scientific progress than positivist physicalism, which in fact seeks to pass off the present reduction of scientific knowledge to physico-chemical concepts as the last word of science. As we see, the problem of objectivity in the philosophy of science is split, so to speak, among the existing levels of scientific knowledge, if not among different sciences. We shall not attempt here to investigate into the general causes of this phenomenon in the development of science, we shall merely take it for granted as a fact. In each doctrine, the concept of objectivity is confined within more or less narrow bounds which have a more or less definite location in the space of modern scientific knowledge and conform to its existing structure. The concreteness of philosophical categories, as we have shown above, has nothing to do with this location reflecting the limitations of each doctrine and, in the end, its subjectivism. The dialectico-materialist interpretation of the objective, which is inseparably linked with the definition of matter as a philosophical category denoting objective reality independent of human consciousness in general, sets but the epistemological framework for this concept and has no meaning beyond the limits of the basic question of philosophy, the one concerning the relation of matter and consciousness. It is not connected with the boundaries of individual sciences or fields or levels of knowledge. It contrasts everything that is subjective to everything that is independent of consciousness. It points out the asymmetry of the relationship between them. The contrast between the objective and the subjective has a purely philosophical meaning. Perhaps like no other conceptual distinction, it sets a clear demarcation line between philosophy and positive sciences, which are in fact indifferent to such a universal division. The independence of philosophical knowledge, its irreducibility to any special science, stands out here with particular clarity, though the specificity of philosophy can also be demonstrated on the example of a number of other problems. The philosophical understanding of the objective as essentially independent of consciousness in general is evidently much broader than its interpretation in the positivist, Popperian, physicalist and scientific realist concepts, which connect objectivity with observability, intersubjectivity, reducibility to physical notions, etc. It should be noted, however, that different versions in the interpretation of objectivity are not always groundless and senseless. The positivist understanding of objectivity, for one, has a certain value within the framework of empirical investigations, whereas the Popperian interpretation of objectivity must be given credit for its attempt to view the positivist solution from a broader socio-cultural perspective and to emphasize the existing demarcation between the individual and general consciousness, etc. It would not be correct to regard them as completely wrong, rather, they are narrow and deformed. To view the problem of objectivity from the philosophical angle, one has to universalize the methods or ideas of special sciences or branches of knowledge and rise above their level, since this problem assumes one form in physics, another in biology, still others in history, theoretical sciences, empirical sciences, etc. Each of these disciplines concentrates on its own specific, topical aspects of the problem and has its own means and ways for its solution. Hence, the first aspect of the problem of objectivity, as it is posed in contemporary philosophy, calls for a dialectical analysis and consists in distinguishing, first and foremost, between its empirical and theoretical levels. Obviously, objectivity cannot be reduced to observability, coherence, one or another degree of the generalization of concepts, etc. Any of the above criteria leads to an unwarranted restriction of the concept of objectivity as it implies independence of the object of investigation from some special kind, form, or level of consciousness, but not from consciousness in general. Yet the concept of the objectivity of knowledge in its philosophical sense presupposes the independence of knowledge from consciousness in general, be it individual or collective. The numerous difficulties involved in the implementation of this criterion do not by any means attest to its uselessness, they merely confirm the well-known truth that the path of true science is not a royal road. The theories asserting the objective character of knowledge but regarding it to be independent of certain forms of consciousness only imply, willy-nilly, its dependence on other forms of consciousness, thus leaving a loophole for idealism. No less untenable are the attempts of some other philosophers proclaiming themselves adherents of materialism to identify matter and, consequently, objectivity with one or several properties of material objects except the sole property of matter with whose recognition philosophical materialism is bound up, the property of being an objective reality, of existing outside the mind. The history of philosophy shows that the single problem of the objectivity of knowledge can and must be solved differently at different levels of scientific cognition. The recognition of this fact is perhaps the starting point of the process of fusion of materialism and dialectics, which reveals the complex and contradictory character of scientific cognition and shows that it cannot be confined to the sensuous, empirical stage. Scientific cognition goes into the depth of processes and phenomena, penetrates the realm of laws and reveals laws of different orders and different degrees of generalization. The criterion of objectivity, which may appear simple and explicit to any investigator in his specialized field, is bound to turn into a complex problem when he enters upon the theoretical level of cognition and finds himself in the jungle of philosophy after the prairie of the macro world. It should be stressed, however, that the observance of the principle of objectivity was and remains the primary objective of modern science. Without the elimination of the subject, however difficult it may be for the investigator, scientific research will lose all meaning. Therefore, recognizing distinctions in the approach to the problem of objectivity at philosophical, theoretical, empirical, and other levels is making but one, though important, step forward. The next step, which is, evidently, the most difficult one, consists in revealing their relationship and defining a method for changing over from a philosophico-theoretical to philosophico-methodological aspect and further to the theoretical and empirical levels of the problem of objectivity. In point of fact, we need some kind of a bridge to pass from the philosophical principle of objectivity to its concrete embodiment in the context of a scientific theory. We believe that the function of such a bridge leading from one level of knowledge to the other in the formulation and solution of the problem of objectivity can be performed primarily by the idea of invariance. The principle of objectivity implies, in essence, the elimination of the subject from the object of investigation. What is the actual meaning of this requirement in the context of a concrete scientific investigation? Should we understand this phrase literally? Significantly, dialectical materialism has never maintained that the requirement of the objectivity of knowledge is equivalent to setting up some kind of an insurmountable barrier between the subject and the object of investigation. Insurmountable in the sense that it prevents any influence of man on the object of cognition and only permits the mirror reflection of reality in his consciousness. Knowledge, wrote Lenin, is the reflection of nature by man. But this is not a simple, not an immediate, not a complete reflection, but the process of a series of abstractions, the formation and development of concepts, laws, etc., and these concepts, laws, etc. embrace conditionally, approximately, the universal law-governed character of eternally moving and developing nature. Thus the dialectics of cognition presupposes man's active penetration, intrusion into reality, his, so to speak, aggressive attitude to it. Here one may ask, how can such an attitude agree with the principle of objectivity? To eliminate the subject does not mean to fence him off from the object of his investigation, though sometimes a specific kind of a barrier, e.g. an aquarium wall, can indeed make for objectivity, like in the case of an observer studying the behavior of fish or sea plants. Nor does it mean to dig a ditch which can sometimes separate an investigator watching wildlife. Eliminating the subject means creating conditions which would not so much prevent him from interfering with objective processes as from distorting them and causing to deviate from their normal course. In terms of epistemology, the subject is a very complex notion accounting for the possibility of human errors, inaccuracies, and prejudices, inadequacy of technical and natural means at man's disposal, as well as of the store of knowledge available to him, the specific features of his perceptions, mentality, etc. It would evidently take several pages to enumerate the elements which make up the notion subject and should be excluded from the notion scientific knowledge. What really matters, however, is not this enumeration, but the obvious fact that man's centuries-old experience must have already developed reliable mechanisms compensating for the subjective aspects of the process of cognition. The elimination of the subject is always aimed, in one form or another, at this compensation and correction of the defects which are inevitably introduced by man in his exploration of the universe. Far from denying the subjectification of reality by man, dialectics considers it inevitable and shows that man transforms reality through his practical, experimental, and even mental activity, since the world, of course, can never be adequately represented in man's concepts. Man is unable to embrace the world in all its inexhaustibility. He is bound to limit the sphere of his investigations to the phenomena which are within his reach. At present, for instance, man is still unable to penetrate the structure of microparticles and has to be content to study their external interaction or to split them in a powerful accelerator. So, insisting on the objectivity of scientific knowledge, dialectics proceeds from the fact that the subject alters the object in the process of its investigation. Yet the objective can only be revealed in the surrounding world if the investigator concentrates primarily on the stable, the recurrent. It is this search for immutable, invariant properties and values that represents the transition from the general idea of objectivity to the theoretical analysis of objective processes and phenomena. While revealing the immutable, the stable in the objects and phenomena under investigation, the natural scientist may not even be aware of the fact that he attains objective knowledge. The above does not mean, of course, that changing properties cannot be objective. If we speak of dynamic processes, the only requirement they should meet from the viewpoint of the principle of objectivity is the constancy of change. Not the change of constancy, but vice versa. Just so. The language of objectivity is translated into the language of invariance. Naturally, a physicist, a biologist or a sociologist cannot divorce the object of investigation from his consciousness. What he can and what he really does and must do is to distinguish between the mutable and the immutable properties of the object during his studies. This bridge from the general philosophical to a particular scientific idea of objectivity has been operable for centuries, though its strength has been frequently subjected to testing. None of the tests, however, destroyed it, nor could do so completely. As a result, the bridge had only gained in strength, simplicity, and elegance. Why, for instance, was its usability called in question at the turn of the 20th century? Because the philosophers erroneously identified matter with the concrete properties of things, but not with their only property of being an objective reality, of existing outside the mind, whereas the physicists were bewildered by the collapse of their habitual concepts. The mass of the electron turned out to be variable, the stationary and impenetrable ether movable, the spatial and time intervals changeable. The world, once stable and reliable, was falling to pieces, matter had disappeared. How did philosophy and physics overcome this crisis? Lenin formulated a philosophical definition of matter in which the criterion of objectivity was connected with the property of existing independently of man's consciousness. Physics found new invariants, giving a new meaning to this philosophical idea. Invariants, wrote Max Born, are the concepts of which science speaks in the same way as ordinary language speaks of things, and which it provides with names as if they were ordinary things. Invariance is the property of immutability in relation to a definite set of physical or mathematical conditions, specifically, to a group of transformations. This property is inherent in individual physical and mathematical values and physical characteristics, as well as in equations and laws of physics. An invariant value can be exemplified, for instance, by the distance between 2 points in geometry, or by value E2H2 in regard to Lorenz's transformations in electrodynamics, though the values of the intensity of electrical fields and magnetic fields prove to be invariant when changing from one inertial reference system to another. Group invariance is a kind of symmetry which is widely used in modern physics, the invariance of equations in relation to groups of Galilean, Lorenz's, and Poincaré's transformations, the symmetry of Schrödinger's operator in relation to the rotational group of three-dimensional space, the symmetry of crystals, the unitary symmetry, etc. A more general case of invariance is covariance, i.e. the property of transformation of a number of physical and mathematical values in accordance with a definite linear law when passing from one reference system to another. Covariance reveals itself in relation to different groups of transformations. It may be inherent both in different values, e.g. vectors, tensors of relative rotations, and in different equations and functions. A covariant value is a value transforming in relation to one of the representations of a group of coordinate transformations being studied. Covariant equations are those which, on being recorded in a covariant form, do not change their appearance in any system of coordinates, though individual physical values incorporated in such equations may be different in different reference systems. The wide use of the notion of transformation group is accounted for by the immutability of a number of physical objects within one or another group, which circumstance makes it possible to define the law of their change during such transformations. A transformation group can be exemplified, for instance, by a finite set of projections of a certain object on other objects known sufficiently well by their properties, e.g. on measuring instruments, experimental facilities, etc. Thus, if we are interested in a geometrical form, i.e. in the spatial structure of an object, we can regard its projections on different surfaces arranged at different angles relative to one another as geometrical transformations of the form of this object. The selection of a set or series of such projections making up a certain group of transformations in the mathematical sense depends on the conditions of the existence of a given system, on its limits or measure, as well as on the concrete cognitive situation and the nature of the task the investigator is confronted with. It is the analysis of invariance and structure carried out with due regard for the objective and subjective aspects of the process of cognition that makes it possible to use the principle of invariance in the solution of such a fundamental epistemological problem as the problem of the objectivity of knowledge. To be sure, it would not be correct to identify the invariant with the objective. Both invariant and variant physical values, as well as their relationships, can be objective in equal measure. Both of them, as has already been emphasized by Einstein, reflect to a degree objective reality. According to Einstein, the difference between invariance and variance does not lie in the same plane as the difference between the objective and the real, on the one hand, and the subjective and the seeming, on the other. If that were not the case, the concept of objectivity would apparently become superfluous. The revelation of invariance and variance is not yet equivalent to the establishment of the epistemological nature of each of these classes of phenomena. The question of the invariant or variant character of different quantities and of their relationships can only be solved within the framework of each individual theory and under the strictly defined conditions of investigation. Invariant values and relationships are direct characteristics of the laws governing the behavior and properties of the objects of a given theory, which are freed from the characteristics relating to the specific conditions of investigation. This also applies to those conditions of investigation which are connected in one way or another with the subject in a given relationship. Hence, the conditions to be additionally eliminated are only those characterizing the subjective aspect of the process of cognition. The object under investigation should be considered theoretically in all possible transformation groups so that its objective presentation in theory may be as full as possible. For instance, in the classical method of description, the absolute length characterizes the property of a body in absolute space regardless of the selected reference system. Recognition of the absolute nature of space and time presupposes the indifference of objects to the subject and to the reference system. Conversely, the relativist description of the space-time interval characterizes the property of a physical object in relation to the selected system of reference. The theory of relativity treats simultaneity as a variant concept. It means that the simultaneity of two events is not regarded as absolute, since it represents not only the relation between the events themselves, but also depends to an essential degree on the selected system of coordinates. It is even more so if the events are separated spatially. In that case, the objectivity of simultaneity can only be attested to by the invariance of space and time in one or another relationship. As we see, variant values characterize relations between the objects of a given physical theory, on the one hand, and the conditions of investigations, on the other. A variant value can have any meaning only within the framework of a given theory and only in relation to definite conditions of investigation. Invariant and variant values represent different aspects of objective reality. Yet for a concrete physical theory, the relationship between them is of paramount importance, as it determines the concrete measure of objectivity attained by this theory. It is not fortuitous that the search for invariance constitutes one of the main tasks of every physical and mathematical theory, and the replacement of old invariants by new ones is indicative of a transition from the old theory to a new, more general one. As a matter of fact, a transition from one theory to another covering essentially the same sphere of phenomena is only possible as a result of transformations revealing new invariants. This mechanism of transformations ensuring the birth of objective knowledge has long been one of the chief secrets of science, the veritable philosophical stone so badly needed by the alchemy of scientific cognition. It is in the process of search for invariance that the system of knowledge is purged of subjective elements and old scientific theories are replaced by new, more objective ones. The change in the relationship between invariant and variant values in favor of the former testifies to the elimination of subjective elements from physical knowledge and is indicative of a transition to a higher level of objectivity, to the expansion of the sphere of objectivity of physical knowledge. The preservation of immutability, invariance of certain values against the background of the mutability, variance of others is a sure sign of the objectivity of immutable values. It appears that invariance is always connected, in one way or another, with objectivity. It does not mean, of course, that invariance always represents the objective content of a theory, but the probability of their coincidence is very high. Being always oriented towards the future, the process of cognition must of necessity have a considerable margin of safety, therefore every invariant in a theory must be regarded as potentially variable. On the other hand, the variable aspects of a theory are to be studied more closely with a view to determining the degree of objectivity they may represent, for which purpose attempts should be made to identify a group of transformations under which certain values in the equation in interest may prove to be invariant. The presence of invariance and variant relationships in a given theory determines the degree of its objectivity, i.e. testifies to the presence of structural characteristics and properties of physical objects whose specific forms of symmetry are disclosed by the given theory under the specified conditions of investigation. If some values or their relationships prove to be variable relative to given transformations, this cannot yet be regarded as attesting to the non-objectivity of the corresponding properties or relationships. It simply means that the question remains open and the investigation should continue. What is variant in relation to one group of transformations may prove to be invariant in relation to another group. Besides, account is also taken of the fact that the very process of change can also be expressed in the language of invariance with the help of its isomorphic transformations. For instance, the melody of a song can be represented by changes in a continuously modulated signal. During the transmission of the signal from the sensors to the central processing units, its form changes with the change of the physical carriers, methods of modulation and coding. Yet the content of the signal, the information carried by it, i.e. the orderliness of the pulses representing the melody of the song, remains invariant, independent of these transformations. It should be specially noted, even in this cursory survey of the problem, that the principle of invariance underlying macro-world theories in a latent form plays even a more important role in the investigation of the micro-world. Though the classical theories can be restructured in such a way as to place this principle in the limelight, they are nevertheless based on dynamic principles expressed in the equations of motion or field. We may assume, without going deep into this subject, that the objectivity of knowledge in the investigation of the macro-world is best represented by the equations of classical mechanics. It is not accidental, therefore, that the decisive role in ensuring the objectivity of knowledge at the macro level belongs to experiment. By contrast, theoretical science has developed its own, specific methods and principles of obtaining objective knowledge, attaching, it appears, special importance to the principle of invariance. As is known, invariance or group symmetry originally played but a secondary role in quantum mechanics, making it possible to obtain only auxiliary data on a quantum system. With the integration of Schrödinger's and Dirac's dynamic equations, however, the situation changed. Soviet scholars U.B. Rumer and AIFET write, the development of physics over the past few years has reversed, as it were, the relationship between the equations of motion and symmetry groups. Now the symmetry group of a physical system has come to the foreground. The representations of this group and its subgroups carry the most important data on the system. Hence, groups turn out to be the primary, the most profound elements in a physical description of nature. As to the concepts of space and time, they play the role of material for the construction of the representations of groups and owe the place they occupy in physics to historical factors only. The equations of motion are assigned the role of conditions superimposed on the vectors of some functional space for singling out irreducible representations of a group or equations of the infinitesimal representation of the same group. This shift of basic concepts does not seem to encourage the idea that each kind of particles and fields should be represented by some equation of motion. What is more, the very universality of the scheme known as the theory of field is called in question. The principle of invariance is also largely accountable for the considerable degree of subjectivism in scientific concepts of space and time. The concept of absolute space and time was used by Newton in two different, though interrelated, senses. First, by absolute space Newton understood the empty and motionless space of the universe, and by absolute time, pure duration corresponding to absolute space. Second, he used the term absolute to characterize the invariance of lengths and time intervals. It is precisely this latter aspect of the absolute nature of space and time which we are interested in here, since it is directly connected with the question of their objectivity. The development of physics showed that the hypothesis of the absolute nature of space and time was narrow and contradicted a number of important scientific facts. For instance, it was not compatible with the principles of electrodynamics. The equations of electrodynamics were not invariant in relation to the Galilean transformations expressing the absoluteness of time and space. When applied to the electromagnetic field, Galilean transformations led to a conclusion that magnetic disturbance was transmitted at different velocities in two opposite directions from a moving source, whereas the equations themselves excluded such a possibility. Subsequently, the narrowness of the Galilean principle of relativity as applied to electromagnetic phenomena was proved experimentally. Michelson's experiments in determining the velocity of light in different directions relative to the moving Earth showed that the classical law of the summation of the velocities ensuing from the Galilean principle of relativity did hold true in relation to the velocity of light. The contradiction between electrodynamics and the results of Michelson's experiment, on the one hand, and classical mechanics based on the Galilean principle of relativity, on the other, was resolved by the theory of relativity. Proceeding from the postulate of the constancy of light velocity and using it as the basis of his theory, Einstein universalized the principle of relativity, calling for the invariance of physical laws for inertial systems, and extended it to all physical processes, including electromagnetic ones. In classical mechanics, the concept of absolute time found its expression in the recognition of absolute simultaneity. If any two events occurred simultaneously in one inertial system of reference, they were also bound to occur simultaneously in another. The conclusion ensuing from the principle of the constancy of light velocity was entirely different. Two events which took place simultaneously in one system of reference could not be simultaneous in another. In other words, simultaneity according to this principle was relative. The relativeness, non-invariance of simultaneity signified the non-invariance of the laws of physics in relation to Galilean transformations. According to Einstein's principle of relativity, the laws of physics are invariant not in relation to the Galilean, but to Lorenz's transformations, these providing direct substantiation for the concept of relativity of space and time viewed separately. Thus the length of a rod turns out to be different in the rest system and in the body axis system of coordinates. Various authors not infrequently see the philosophical significance of the theory of relativity in that it showed the variant character of space and time. It is correct in the sense that this theory indeed revealed new links and relations which had not been taken into account by classical physics, and thus gave a broader and more profound picture of the dialectics of time-space relations. Such a general appraisal, however, needs to be somewhat specified. First, it would not be correct to regard the concept of absolute space and time as an erroneous, metaphysical picture of the world. This concept stands in the same relation to the objective world as do all classical physics and its laws. It is a permissible idealization of reality, its approximate reflection in relation to speeds which are practically negligible as compared with the velocity of light. It is applicable to situations in which the velocity of light can be regarded as practically infinite. Second, the significance of the theory of relativity cannot be reduced to establishing the relativity of space and time. From it ensues not only the invariance of space and time separated from each other, but also the existence of a new invariant, the time-spatial interval. Einstein and Infeld write, the world of events forms a four-dimensional continuum. There is nothing mysterious about this, and the last sentence is equally true for classical physics and the relativity theory. Again, a difference is revealed when two CS moving relatively to each other are considered. The room is moving, and the observers inside and outside determine the time-space coordinates of the same events. Again, the classical physicist splits the four-dimensional continua into the three-dimensional spaces and the one-dimensional time continuum. The old physicist bothers only about space transformation, as time is absolute for him. He finds the splitting of the four-dimensional world continua into space and time natural and convenient. But from the point of view of the relativity theory, time as well as space is changed by passing from one CS to another, and the Lorentz transformation considers the transformation properties of the four-dimensional time-space continuum of our four-dimensional world of events. The qualitative distinction between the space-time relationship in classical physics and the four-dimensional continuum in the relativity theory is that in the first case space and time are treated as existing independently of matter and motion and separately from each other, their connection being entirely external, whereas in the second case they penetrate each other and make a single whole. On the one hand, the concept of time is incorporated in the definition of the spatial interval, which is the distance between 2 points localized simultaneously. The relativity of simultaneity makes the spatial interval dependent on time. On the other hand, spatial components are incorporated in the definition of time. The time of two inertial systems is expressed through an equation incorporating a spatial coordinate. Since this coordinate is different for different systems of reference, time turns out to be dependent on space. Hence, the space-time continuum in the theory of relativity is not a mechanical combination of space and time connected with each other through external links, but an integral whole. Fused in a single continuum, space and time do not lose all of their independence. However, from absolute this independence turns into relative. Space and time become, as it were, sections of a four-dimensional continuum. The exposition of the invariance of the space-time interval was simultaneously a substantiation of the idea of the objectivity of space and time in the context of a new physical theory. A similar function was subsequently performed by the general theory of relativity. The second aspect of the problem of objectivity, as distinct from the first, considered above, calls for special dialectical analysis and pertains to the development of scientific knowledge. After the crisis in the late 19th and early 20th centuries, the current scientific and technological revolution has once again demonstrated the relativity of scientific knowledge, its concepts and theories. Centuries-old and seemingly inviolable fundamental concepts and ideas of physics, chemistry, biology, physiology, psychology, and other sciences are undergoing a process of thorough revision. The relativity of fundamental concepts testifies to the historical character of the process of cognition. As we have seen, the present-day breakdown of scientific concepts, like in Lenin's time, arouses the feelings of uncertainty among natural scientists and philosophers, particularly those under the influence of positivist traditions, and makes them question the very foundation of science, the objectivity, stability, and value of scientific knowledge in general. In this context, the relation of the principle of objectivity of scientific knowledge to the principle of its historical development acquires special significance. Analyzing the crisis in natural science at the turn of the 20th century, Lenin showed that the relativity of scientific knowledge was a manifestation of its dialectical development. Yet it is only one aspect of scientific knowledge which must not be torn out of the broad historical context of the development of science. On the contrary, it should be considered in connection with other aspects and features, particularly with relativity's opposite, viz., the absoluteness of scientific knowledge. Should we assume relativism, an objective and necessary aspect of scientific development that it is, as a foundation of the theory of knowledge, and regard it outside and independent of absoluteness, we shall arrive, as was pointed out by Lenin, at absolute relativism, which sees in the history of cognition a process of endless change of concepts, none of which can give a true reflection of objective reality. In fact, the recognition of the relativity of knowledge is not equivalent to the denial of its objectivity. One should not, as Lenin pointed out, confuse the question of the objectivity of scientific knowledge with the question of its fullness, and identify objective knowledge with exhaustive and absolute knowledge. Absolute and relative truths do not oppose each other as mutually exclusive, incompatible characteristics, they mutually complement each other. For dialectical materialism there is no impassable boundary between relative and absolute truth. Any knowledge contains objective truth to the extent to which it gives an adequate reflection of objective reality, and to acknowledge objective truth, i.e., truth not dependent upon man and mankind, is, in one way or another, to recognize absolute truth. From this viewpoint, relative truth is also objective truth, and only differs from absolute truth in that it is but a particle, a grain of the latter, in the sense that it represents the content of absolute truth incompletely, partially. Absolute truth, in turn, is the sum total of relative truths, and each stage in the development of science adds new grains of knowledge to this sum. Speaking of the dialectics of the relative and the absolute in cognition, one should bear in mind yet another important feature of their relationship, namely, that it represents continuity in the process of scientific cognition. In the course of its historical development, science forms a more and more complete and adequate picture of natural and social reality. The growth of scientific knowledge consists therefore in a steady expansion of the sphere of truth represented by a succession of theories replacing one another. Summing up his analysis of the dialectics of the relative and the absolute in the process of cognition, Lenin wrote, "Dialectics, as Hegel in his time explained, contains an element of relativism, but is not reducible to relativism, that is, it recognizes the relativity of all our knowledge, not in the sense of denying objective truth, but in the sense that the limits of approximation of our knowledge to this truth are historically conditional." The ideas expounded by Lenin over 70 years ago are not less, if not more, topical today. Absolute relativism, reanimated in a number of the latest bourgeois concepts of the philosophy of science, including critical realism and the works of some representatives of the historical trend, has now acquired some new aspects. As distinct from the earlier period, when absolute relativism was mainly traceable to gaps in scientific knowledge, the present-day relativists more and more frequently involve the cultural historical determinism of theoretical thinking. Justly emphasizing the dependence of scientific knowledge on universal socio-historical factors, representatives of the above-mentioned and other post-positivist doctrines seek to prove that theories relating to one and the same sphere of knowledge but developed in different cultural and philosophical contexts are incommensurate with one another. In their opinion, scientific revolutions represent so profound a turn in scientists' views that there can be no question of any continuity of old and new theories. Yet the history of science points to the opposite and demonstrates various forms of such continuity. The methods whereby a new theory assimilates and deepens the objective content of its predecessor can be roughly classified under two categories. In the first category, the continuity of the new and old theories is realized through the transfer of certain elements of the old theory into the structure of the new one. These elements may include not only empirical data, but also certain theoretical concepts. For instance, the general theory of relativity borrows the variation principles, the principle of the equivalence of inert and gravitational masses, from the classical gravitation theory. In the second category, which is of a more fundamental and general character, the continuity of the laws formulated in the old and new theories assumes the form of a limit transition, i.e. the laws of the new theory pass into the laws of the old one regarded at their limiting case. Thus, if we assume Planck's constant to equal 0, the Schrödinger equation, the basic one in quantum mechanics, transforms into Hamilton-Jacobi's canonical equation of motion. Scientifically grounded laws and theories have deep roots and exercise lasting influences, otherwise theoretical knowledge would be simply inconceivable. In this connection a question naturally arises: what is the source of the tenacity of a scientific theory in general? Why does it preserve its explanatory and forecasting powers over a prolonged historical period? The mechanisms pointed out by the well-known American philosopher and historian of science Thomas Kuhn in his book The Structure of Scientific Revolutions are psychological, rather than epistemological by nature. Kuhn attributes the stability of a paradigm as a model for the theoretical explanation of facts to the specific psychology of the scientific community, which shows a guarded attitude to a new theory and is never too fast to support it, as well as to the unwillingness of some quarters in this community to part with the habitual stereotype of causal explanations and predictions. Such an explanation appears to have certain grounds, though the scientist's psychological motives need a more careful examination in each particular case. Yet far more important, in our opinion, is the methodological aspect of this problem. From the epistemological viewpoint, the stability of theories derives largely from the fact that each of them participating in causal explanations and predictions rests on definite premises. Unlike the theory itself, which is thoroughly elaborated, its premises are found with comparative ease and, as a rule, are hypothetical by nature. Therefore, if the predictions or explanations made on the basis of a given theory prove to be erroneous, the premises are rejected with comparative ease. Newton's gravitation theory, for instance, was considered to be irrefutable for over 2 centuries. When it sometimes failed to come up to expectations, it was not the theory itself but its premises that were called to account. Thus the discovery of an error in the calculations of Uranus' orbit based on the theory of gravitation did no harm to the theory, it was shielded by the premises which performed their function of a lightning rod. As is known, John Adams and Urbain Le Verrier traced the error to the influence of the hitherto unknown planet which had not been taken into account by the then existing system of assumptions. Should a theory happen to lose its ability to predict and explain events, its prerogatives can be subsequently restored if a new set of conditions is found under which the theory regains its powers. In many theoretical disciplines, scientists prefer to preserve the theory's right to predict and explain events and put off the question of its incompatibility with certain facts. Hence, theories retain their explanatory powers even when some explanations prove to be patently erroneous. Such theories are later modified in accordance with new data which appeared at first discordant, and new assumptions are made to support them. The fruitfulness of the backing hypothesis method can be exemplified by Pavlov's theory of conditioned reflexes. The analysis of the structure of this theory shows that it is sufficiently resistant to some contradicting facts. For instance, an animal trained to respond in a definite way to a certain stimulant far from always follows the exact pattern of behavior required of it. Its response is usually slow or even incorrect. That does not mean, however, that the very first deviation from the forecast made on the basis of the theory of conditioned reflexes should be seized upon as a pretext for refuting this theory. In such cases, the usual tactics of a scientist consists in shielding the adopted theory with an auxiliary hypothesis and alleging interference with the required conditions of an experiment rather than in discarding the theory itself. A supposition can be made, for instance, that the animal's nervous system fails for some reason or other to pass through the excitation caused by a corresponding stimulant or even exerts upon it a certain suppressing effect. Indeed, numerous experiments carried out by neurophysiologists showed that excitation can really be suppressed in the nervous system owing to feedback via various nervous circuits with their numerous bends and loops. The hypothesis of the suppression of excitation in nervous circuits serves, on the one hand, as an additional assumption backing up the idea of conditioned reflexes, and, on the other, turns out to be an independent theory subject to additional testing. This hypothesis preserves the validity of the conditioned reflex theory, making it a durable and effective instrument of causal explanations and predictions in the physiology of higher nervous activity. Hence, owing to various assumptions, scientific theories provide a high degree of stability for explanations and predictions based upon them and cover a broad field of various phenomena and processes. As we see, a transition from one scientific theory to another is a much more complex process than a simple negation of the old theory by a new one. Some elements of the old theory are revised or even altogether excluded from the content of a more developed theory. Other elements are carried over from the old to the new theory without any change or in the form of a limit transition, ensuring the necessary continuity and comparability of different stages in the development of science. The third important aspect of the problem of objectivity, or, more accurately, of the dialectics of the objective and subjective, which is ignored both by the critical rationalists and scientific realists, is the relation of the objective content of our knowledge to the abstractions instrumental in the development of scientific concepts and theories, i.e. the dialectics of the objective and the subjective in the very content of scientific knowledge. As we have seen, positivism regarded sensations, sensory data as the only reality, i.e. identified them with reality independent of our consciousness, and thus discarded altogether the question of the approximateness, incompleteness of human knowledge. As to critical rationalism, it defends the thesis of the complete arbitrariness of the abstractions and assumptions needed to construct a scientific theory. Both these schools, undialectical as they are, proved unable to solve the problem of objectivity. The substantiation of the objectivity of scientific knowledge cannot be limited to the analysis of the relation of the content of this knowledge to the objective world, though it is, undoubtedly, the major part of the task. As is known, cognition is not a mirror image of reality, but, using Lenin's words, a process of the formation of abstractions, laws, etc. In the process of cognition, particularly scientific cognition, the investigator sets himself an aim, defines the object of investigation, disengages himself from all that is inessential and likely to hamper his reasoning and experimenting, etc. Besides these operations, cognition presupposes the breaking away of thought from reality, the flight of fancy, the image-bearing thinking. It might seem that all this mental activity is bound to reduce to zero any objectivity of knowledge, since it represents nothing but the subjective factor in the process of cognition. Moreover, many of the above operations, consisting essentially in the creation of abstractions, must lead of necessity to the distortion of reality, to obvious errors and miscalculations. The objectivity of knowledge might seem incompatible with the constructive activity of thought, with its active interference in the course of events. Yet it would be unwarrantable pedantry to disparage scientific knowledge because of its subjective component, which does involve the possibility of errors and distortion of reality. In point of fact, scientific knowledge would be simply impossible without this component. Abstractions which are prerequisites for scientific knowledge deserve therefore special attention, the more so as many difficulties connected with the problem of objectivity derive from the incorrect understanding of their character and role. Coincidence of a notion and its object, theory, and reality is a complex, dialectically contradictory process. Between the object and the knowledge of the object lies the sphere of man's activity, his goal-oriented actions aimed at transforming and cognizing the surrounding world. Lenin wrote, "Here there are actually, objectively, three members: 1. Nature, 2. Human cognition, the human brain, and 3. The form of reflection of nature in human cognition, and this form consists precisely of concepts, laws, categories, etc." Pointing out that the main drawback of the theory of knowledge in pre-Marxian materialism consisted in its inability to apply dialectics to the theory of reflection, Lenin specially emphasized in his philosophical notebooks the need for a dialectical approach to the theory of knowledge, to cognition as a historically developing complex process mediated by the collective material and spiritual activity of mankind and by the existing system of relations between the individual subjects of cognition. The elaboration of the concepts of reflection was thus connected with the development of much more flexible and profound views on the cognitive activity of man. Cognition is indeed reflection, yet it is the reflection of a special kind which could only be explained after a radical revision of the epistemological concepts of pre-Marxian materialism. The revised concept, far from breaking off with the basic principles of the materialist approach to the process of cognition, was to make materialism even more flexible and consistent. The new, more profound understanding of the process of cognition was to be based on the idea of unity of reflection and activity, which implied the dependence of human knowledge on socio-historical conditions. This new concept threw entirely new light on many traditional problems of the theory of knowledge and made it possible to explain the mechanism of the reflection of objective reality. Despite the broad variety of views on the origin of scientific knowledge in pre-Marxian materialist philosophy, common to all of them was the conviction that the solution was to be achieved through investigating the direct action of objects on passive individual consciousness. The formation and growth of knowledge were only attributed to the operation of those factors which manifested themselves in the influence of objects on the sensuousness of the individual, and no account was taken of all other determinants of the process of cognition: the dependence of the cognitive image on links with other branches of knowledge, on the existing historical substantive generalizations and schematic ties and relationships revealing themselves in man's practical experience, on the forms and methods of investigations, etc. In point of fact, it was not understood that any object could only become a source of knowledge after being mediated by the practical activity of social man and by the previous history of cognition with its objectifications, schematizations, and idealizations. The new ideas constantly emerging in the course of the development of science are always conditioned, in one way or another, by the cognitive situation in the entire system of scientific knowledge. The progress of science is based primarily on the available knowledge, on the existing collective forms of cognitive activity objectified in the language, in scientific systems, etc. It is the active character of specifically human perceptions, their unity with social practice, the need for a dialectical integration of individual sensory data in a single system of perceptions that was referred to by Lenin when he characterized sensation as a subjective image of the objective world. The social norms and prerequisites for cognitive activity play even a more important role in the formation of an objective epistemological image at the theoretical level of investigation. Theoretical thinking is known to be based on a complex system of idealizations, including a special layer of mental structures, the so-called ideal objects which have no analogues among empirical objects, properties, or relationships and which function and develop in accordance with their own laws operative in the field of theoretical knowledge only. As long as a layman inexperienced in philosophical intricacies remains within the sphere of conventional ideas, his attempts to see through a tangle of events and find a clue to his current problems can hardly induce him to take a conscious stand on either side of the barricade between materialism and idealism. Things begin to clear up when he passes beyond the limits of his experience and finds himself confronted with unusual phenomena and processes or encounters violations of habitual causal relationships. Under such conditions, an individual who is not prone to religious prejudices begins to realize the complete groundlessness of the illusion that his consciousness dictates laws to nature or forms a chain of events by determining the order of causes and consequences at his own will. It is perhaps after being within a hairbreadth of death in an earthquake or after suffering a heavy shock from a flood as a result of an unexpected torrential rain that an individual keenly realizes the objectivity of the surrounding world. A scientist, however, attaches far greater importance, of course, to those arguments which are adduced by nature for or against his ideas and theories. Isn't, for instance, the refutation of the once popular theory of the existence of water canals on Mars, maintained till quite recently, yet another argument in support of the objectivity of our knowledge? Aren't the discoveries of quantum mechanics and of the physics of elementary particles which shattered the foundation of classical science convincing proof of the objective nature of scientific cognition? The very unexpectedness, bizarreness of the most important discoveries of modern science, as well as the apparent intangibility of many scientific ideas testify to the fact that our knowledge of nature does not shut itself up in its own shell, but reflects with an ever-increasing degree of accuracy the real, objective properties of reality. As is known, the graphic representation of the surrounding world is connected with the specific features and conditions of man's cognitive process. Yet the phenomena under investigation exist independently of human consciousness and therefore need not necessarily assume the graphic, tangible form as understood by man. The objectivity of the existing connections and relationships in the world is also demonstrated by the fact that man often begins to realize their significance for his life and practical activity too late and, being unaware of the existence of certain links of extensive causal chains in nature and society, proves incapable of foreseeing all the consequences of his interference with natural processes. This aspect of the objectivity problem, for one, gives mankind no little trouble at present on account of the irrational use of natural resources by previous generations, the upsetting of the natural balance of water and energy reserves, and environmental pollution. The very fact that people often find themselves unable even to formulate a problem before it thrusts itself upon them clearly demonstrates the objective nature of causal relations, social and natural laws which do not depend on when and how man becomes aware of their operation. Scientific knowledge is but a more or less adequate reflection of objective relations between phenomena which is shaped and mediated by the no less objective needs of society. Special importance, in our opinion, attaches to the recognition of the objectivity of links and relations. The existence of objects outside man's mind is seldom negated even by inveterate agnostics adhering to Hume's tradition. Nor is it denied by positivism and modern philosophical science. What they do not accept is the objectivity of links and relations, particularly causal relations. This necessitates considering in somewhat greater detail the objective character of causal explanations, forecasts, and laws in the general context of the problem of objectivity. The concept of causality represents in the most general form various relations in nature and society between phenomena, one of which determines or produces the other. Objective in such relations are not only cause and effect as definite objects, events, or phenomena, but also the relations themselves, which are independent of consciousness whatever their nature, material, energetic, informative, etc. It may look strange to the uninitiated that this brief statement could have caused and is still causing sharp debates which involve not only the methodology of scientific cognition, but also extend to the problems of social development and even ideological struggle. Yet universality is characteristic of all philosophical categories if they are truly scientific and represent objective reality. Viewed in terms of problem intensity, they may be likened to an iceberg with a huge submerged portion. The problems they contain in embryo reveal ever new facets in each successive historical period. There is apparently nothing ambiguous about the word produce, particularly when we use it in the context of our everyday experience or in relation to macroscopic processes. In its conventional applications, it conveys the ideas of the real direction of a process as a result of which one phenomenon produces another, of the succession of cause and effect in time, of their real similarity and unity of their nature. Yet each of these aspects of a causal relationship turns into a complex and difficult problem when we turn to objects studied by modern science. How can we single out cause and effect from a multitude of other objects and phenomena accompanying the process under investigation, and this in such a way as to express correctly the real relation between them? What is the meaning of the word to produce in a scientific context if there is no possibility to trace the entire process from cause to consequence? Is this process continuous or intermittent, necessary or accidental, transitive or intransitive, and so on and so forth? Most of these problems do not even arise in our everyday consciousness, nor are they implicated in the philosophical investigations of the positivist and realist schools. For positivism, which regards sensations or complexes of sensations as the only reality a scientist is concerned with, causality is a purely psychological problem limited to the formation of associations in the process of observation of a regular sequence of events. Hence, from the positivist viewpoint, the problem of causality is devoid of any philosophical meaning and comes within the scope of concrete psychological investigations. Critical rationalism regards causality in terms of the deduction of explanations and predictions from more general knowledge. It therefore does not recognize the problem of the correctness, accuracy of these causal explanations and predictions of the effect of one or another cause, since effect is a logical sequence of cause, provided there is a more general law. The problem of the relationship between discontinuity and continuity is discarded by the school in a similar manner. The causal relationship being the result of a logical inference must be continuous and transitive by virtue of its definition. Popper, for one, rejects also the problem of the relation of causality to chance and necessity, since the very concept of causality implies necessity as its logical component. By contrast, scientific realism recognizes the objective existence of causal relations, supposing them to be directly mirrored in scientific knowledge. The philosopher's task is thus restricted to the generalization of the available knowledge of the physical, biological, chemical forms of causal relations and to the classification of these numerous forms, whereas the establishment and investigation of their specificity is left to natural scientists themselves. The difference between the philosophical and natural scientific knowledge of causality thus lies in the degree of its generalization only. Paradoxical though it may seem, both scientific realism and positivism discard the same philosophical problems. This coincidence, as we have shown earlier, springs from the identification of knowledge and reality which is characteristic of both positivism and scientific realism despite the latter's obviously materialistic platform. The only difference between them consists, perhaps, in that positivism deduces reality directly from knowledge, whereas realism deduces knowledge from objective reality. Both philosophical trends, as we see, arrive at the same conclusion, though their paths are different. Positivism eliminates materialism as a principle of scientific investigation, whereas realism eliminates dialectics. One lays the stress on the subjective, the other denies its role in the process of scientific cognition. Here we can see once again that materialism and dialectics are inseparable and that one cannot exist without the other. To be sure, the physicists or biologists are only interested in the objective content of a process and seek to establish causes and effects, pursuing their immediate practical aims. As to the philosophers, they have a different problem to solve. They should separate the objective content of knowledge from those subjective elements which are inevitably introduced by the scientists in causal explanations and predictions. Assuming the physicist's or biologist's attitude, the philosopher not only abandons his field, but attempts to pass for a philosophical truth something which has absolutely no right to claim this title. Willy-nilly, this stand is tantamount to the distortion of reality in a philosophical sense. Of course, in dealing with causality, the philosopher should not close his eyes to the objective content of the knowledge gained within the framework of special sciences, such as physics, chemistry, and biology, otherwise he would open the door for idealism and subjectivism in science. Yet his real task, which has already been considered earlier, consists in specifying the subjective aspects of causal explanations and predictions. In the context of the basic question of philosophy, i.e. the relationship of matter and consciousness, the mind and nature, the philosopher ought to disclose all subjective prerequisites for scientific investigation, since this task lies outside the scope of the problems tackled by the scientists themselves. From the philosophico-theoretical viewpoint, the problem of objectivity consists in revealing the subjective elements of causal explanations and predictions in special scientific investigations and in disclosing after that the interdependence of the objective and the subjective, their dialectics in the process of cognition. Hence, the development of knowledge is characterized by a trend towards comprehending the real object of cognition as a unity of all its aspects and toward integrating all the cognized fragments of reality in a single objective system revealing its different aspects before the cognizing subject. The realization of this trend calls for the investigation of the forms of interaction of each object with other objects, as well as with the cognizing subject himself. The objectivity of knowledge is therefore made contingent on the understanding of the role of the subject in the process of cognition, particularly the role of measuring operations, the instruments used by the investigator, his system of reference and methods of coding the attained knowledge. In his everyday work, a physicist, a chemist, or a biologist usually encounters this problem in its philosophico-methodological aspect while seeking for concrete, specific means to single out the objective content of causal relations in reality itself, in actual processes taking place under natural conditions. It is the more important as the real problems and difficulties facing science in the field of methodology often stem not only from the erroneous understanding of causality, but also from the disregard or underestimation of the abstractions and assumptions forming the framework of the concept of causal relations. From the methodological viewpoint, i.e. from the viewpoint of the effective solution of modern scientific problems pertaining to the principle of causality, it is important to take account not only of the objective content of the concept of causality, but also of its subjective aspect or, more specifically, of all the intricacies in the causal relationship represented by the dialectics of the objective and the subjective. Indeed, to establish a causal relationship between events A and B and to explain event B by pointing out its cause A or to predict possible consequences B1, B2, etc. of known cause A, one must not only indicate the corresponding signs of causality, but also disengage himself from all other events except A and B in the given space-time continuum. In order to understand details, rote angles, we must detach them from their natural or historical connection and examine each one separately, its nature, special causes, effects, etc. An abstraction of this kind resorted to in the establishment of a causal relationship is in fact a routine mental operation often performed in everyday life. For instance, watching the collision of billiard balls, we have no difficulty in identifying the impact of one ball as the cause of the movement of another. In doing so, we discard mentally such factors as the friction of the balls against the surface of the table, the convection airflows, and others, since we know from experience that they cannot have any essential influence on the position of massive billiard balls. Similarly, we say with certainty that on a summer day a stone is heated with sunbeams, but not with the light of distant stars, though we know that their light also reaches the Earth's surface. Yet its effect is negligible as compared with the radiant energy of the sun, therefore we simply disregard it in our explanation. In dealing with causal relationships, such abstractions are used so often that they become habitual and seem quite natural. The ease with which they are created and their practical value produce an illusion that, being quite justifiable in one or several cases, they must be quite relevant in all other similar situations. It is only after we are confronted with a complex situation that we begin to realize the full extent of the difficulties that have to be overcome if we want to establish the cause or effect of a given event in the tangle of a multitude of other objects and phenomena. What is the cause, for instance, of the appearance of deserts in the once flourishing regions of Central Asia? No doubt the cause does exist, though it is evidently represented by a complex system of different factors. To answer this question, we must study a tremendous amount of natural history material and use a great many different experimental means and methods. We must carry out, for one, a geomorphological analysis of water reservoirs, register the climatic changes in the region in interest, study the structure of the topsoil, and so on and so forth. It is only after we complete such research that we shall be able to discard inessential factors and construct a more or less adequate explanation. Why should the task be so complex in this particular case? Is it because the investigator is required to exercise special care in order to reveal the signs of a causal relationship? Rather on the contrary, such signs are too numerous and the problem consists in selecting those of them which are characteristic of the given concrete situation. The abstractions used in identifying cause and effect play an essential role in the explanation and prediction of various phenomena. Should such abstractions prove impossible for some experimental or theoretical reasons, no correct explanation or prediction of events on the basis of causal dependence can be provided. In other words, the establishment of a cause-effect relation is conditional on the accomplishment of all necessary abstractions. The abstractions connected with the concept of causality will only be valid if the investigator observes certain general rules of which we shall indicate at least three. First, invariable conditions should always be fenced off, since cause and effect should be variable factors by definition. Second, if all or many conditions are variable in one or another respect, the changes regarded as signs of a causal relationship must be different by their quality from all other changes in the given space-time continuum. Third, the influence of attending factors must be far less pronounced than the influence of the cause on the effect, the difference in their intensity being such that the attending factors could be disregarded without any appreciable effect on the results of the investigation. The above rules of abstraction impose certain limitations on the objective conditions of the investigation of relationships in interest and, if observed, warrant the qualification of such relationships as causal. The observance of these rules takes the form of various assumptions which relate to the conditions of cognition and are stated in relevant scientific texts. The strict observance of these rules when identifying cause-effect relations guarantees the success of any causal explanation or prediction. A change of B that follows a change of A cannot yet be regarded as proof of the causal dependence of B on A unless the above rules are observed. To be sure, the fulfillment of abstraction rules is often made impossible by objective reality itself. In many cases the scientists would probably prefer experiments to the conditions provided by nature for investigation. What is an advantage in one cognitive situation may turn into an obstacle in others. Noting this specific feature of the process of cognition, the Soviet scholar, V.A.M. Bartsumayan, writes, a physicist confronted with an unknown phenomenon usually repeats his experiment to establish the dependence of the phenomena in interest on those conditions under which the experiment is staged. He has a possibility not only of studying these conditions in every detail, but also of changing them. Things are quite different in astrophysics. Having chanced to observe an unusual phenomenon only once, we can neither control the external conditions under which it took place, nor repeat it at will. Sometimes we do not even have any idea of the condition and circumstances attending the phenomenon we have observed. In most other fields scientists are usually capable of creating artificial conditions which meet the abstraction rules. The aim of an experiment in this case is to show that a change of one object or phenomenon causes a corresponding change of the other object with other conditions being invariable. It is precisely the preservation of the constancy of all other conditions that ensures the observance of the abstraction rules. If the experimental check of a causal dependence is impossible for some reason or other, the investigator can meet the requirements of the abstraction rules by resorting, for instance, to appropriate mathematical means. Suppose, we want to prove a causal relation between the uniform expansion of a rubber ball during an increase of its internal pressure and the behavior of a molecule in a closed vessel. A uniform expansion of the spherical walls testifies to the equality of gas pressure on the vessel walls. Now, how shall we account for this equality if it is known that gas consists of individual molecules moving chaotically within the given volume? In our explanation of the uniform expansion of the vessel, we in fact abstract ourselves from the details of the trajectory of an individual molecule and from the results of the molecule collisions. Do we have the right to make such an assumption? It turns out we do. When we deal with a large number of molecules, we may take it for granted that each molecule stays in any point of the given volume during equal periods of time, since there are equal probabilities that any molecule can get to any concrete region irrespective of its location. As a result of a great number of chaotic collisions, not a single molecule can stay next to another one. Consequently, each molecule acquires a high degree of independence in its movements relative to other molecules. Since accidental collisions tend towards complete compensation, conditions are realized for the application of the concept of causality to the given relationship in full compliance with abstraction rules. Now, what happens when these rules are not observed? Should the researcher fail to take them very seriously, the results of his investigation are bound to be distorted and he may not even be aware of it. Suppose, we want to apply Hooke's law to the relationship between the strain in a steel bar and the pressure applied to it, disregarding the fact that this causal relationship obtains within definite pressure limits only, which are different for different metals. It stands to reason that the explanation itself and the predictions of a concrete strain as a function of the corresponding pressure value will prove erroneous. A similar problem arises in defining the wing configuration in an airplane design. As long as the airplane speed was not high, the designer was justified in regarding air as incompressible liquid. Of course, this assumption was but a crude approximation to real processes, but it could be tolerated as the resulting error was practically negligible. However, when it became necessary to define probable airplane characteristics at high speeds, the hitherto justifiable assumption lost its validity. Account had also to be taken of many other forces arising due to friction, air vortices, vibration, etc. The task of accurate prediction and calculation became much more complex. Consequently, the rules of abstraction have acquired special importance, and failure to observe them is likely to result in serious errors. The assumptions which relate to the conditions of investigation and are used in the analysis of any causal relationship constitute a subjective element in the concept of causality. The admission of this fact calls for a very thorough philosophical analysis of the dialectics of the objective and the subjective in causal explanations and predictions. It is important to understand, first, that the share of subjectivity in such explanations and predictions is so negligible that it cannot jeopardize their objectivity. Second, the introduction of certain subjectivity in such cases is quite justifiable, since the use of abstractions in scientific explanations and predictions is necessitated in each particular case by quite definite objective conditions. It means that the concept of causality calls for at least a twofold substantiation. First, it is necessary to prove the validity of the very idea of causal relationship which underlies its definition. Second, it is necessary to prove the soundness of the abstractions and approximations resorted to. Significantly, from the methodological viewpoint, this latter set of arguments is not less important than the identification of the causal dependence itself, and should be presented independently of the former set of arguments. Here the study of causal relationships reveals one of the most curious manifestations of the dialectics of the subjective and the objective. On the one hand, the singling out of the signs of a causal relationship is a subjective act aimed at investigating and analyzing the objective world. Any denial of the subjective character, goal orientation, and selectivity of the scientific investigation into the cause-effect relationship would be untenable. On the other hand, this subjective act is by no means arbitrary, it is prompted by objective conditions. As regards its motives, they are rooted, in the final analysis, in the practical activity of man. The active role of the subject in the processes of investigation, which manifests itself in experiments, hypotheses, suppositions, assumptions, use of various theoretical and mathematical means, is an indispensable condition of scientific cognition. The tremendous successes achieved by science in the cognition of the world would have been impossible without man's selective approach to reality, without his conscious use of appropriate means and methods in the process of cognition. However inaccurate the approximations, it should never be forgotten that the final result of the investigator's activity is the creation of a scientific picture of the world which helps man to reflect and transform reality through his practical activity. All this is fully applicable to the investigation of objective causal relations. At the same time, one should bear in mind that the singling out of a causal dependence from the entire system of complex objective relations and the disregard of all other conditions cannot but distort the integral picture of the world, since there are no absolutely isolated systems implicitly postulated by the concept of causality. Noting the complex, dialectical character of the cognition of the universal connection of phenomena, Lenin wrote, "The human conception of cause and effect always somewhat simplifies the objective connection of the phenomena of nature, reflecting it only approximately, artificially isolating one or another aspect of a single world process. Being an abstraction, every concept, causality including, tends to distort reality." The attitude to this indisputable fact is different on the part of pessimists and optimists in science. The former say that our knowledge is an endless chain of errors and delusions, whereas the latter do not view the situation as tragic, though they do recognize it to be contradictory, sometimes even dramatic. Indeed, there is no ground for mistrusting science only because its results are not ideal. The history of science provides numerous examples when such difficulties were successfully overcome. In view of the extreme epistemological complexity of the concept of causality, we should reconcile ourselves to the inevitable inaccuracies in any causal explanation and prediction. The scientist's task is to reduce such inaccuracies to a minimum and take full advantage of the effective means now available to him in order to neutralize his errors. It should be noted in this connection that inaccuracies can sometimes be disregarded altogether without any detriment to the validity of causal explanations. For instance, in everyday life we readily accept the explanation that water freezes as a result of the ambient temperature decrease to 4 degrees C, though more accurate measurements made under different conditions will undoubtedly reveal a certain scatter in thermometer readings, even if measurements are made in one and the same place but at different times, or at one and the same time but with different water samples. Why do we tolerate such an inaccuracy? Only because all other factors we close our eyes to are not essential in the given situation. We may disregard, for instance, the influence of admixtures in water and the probable variation of atmospheric pressure, which is also known to affect liquid freezing processes. In the example under consideration, we only single out what we are interested in at the moment, namely, only two most essential events, and neglect all other factors and accompanying conditions. If the quantity of admixtures in water remains within normal limits and the ambient pressure is not very much different from normal, the error in the explanation of water freezing by a decrease of ambient temperature to 4 degrees C will not be essential. Generally speaking, the scientist has every right to change the conditions of his investigation in accordance with the situation and use to this end any conceptual or mathematical means at his disposal, provided, of course, that he strictly observes the rules of abstraction, avoids any arbitrariness in his causal explanations and predictions, and takes care not to distort living reality. The objectivity of the principle of causality, however, consists not only in that it reflects certain aspects of reality and that the selection of certain events as causes and effects is prompted by the objective conditions of cognition. The very motives of this selection are always rooted in the material, practical activity of people and, in the end, in the entire system of social production. Moreover, it is none other than this practical activity that passes the final judgment on the objectivity of causal relations. This idea has been very clearly expressed by Engels. The first thing that strikes us in considering matter in motion, he wrote, is the interconnection of the individual motions of separate bodies, their being determined by one another. But not only do we find that a particular motion is followed by another, we find also that we can evoke a particular motion by setting up the conditions in which it takes place in nature. In this way, by the activity of human beings, the idea of causality becomes established, the idea that one motion is the cause of another. It is precisely the activity of human beings, their social practice, that frees our knowledge from subjectivity, gives our abstractions flesh and blood and integrates them into its great concreteness. It is only through practice, by including the cognate link of a causal relationship, as we understand it, into the objective, universal system of relations that we test the truth of our knowledge. Should it fit into the system without disturbing the course of natural processes, we shall have every right to regard our mental operations and abstractions, even the most daring ones, as completely justifiable. Conclusion. By Igor Naletov. The scientific and technological revolution has proved to be a serious test not only for some general and special scientific theories, but also for many philosophical schools and trends concerned in one way or another with the scientific explanation of the world. Positivist philosophy, which pulled through many difficult periods in the course of its long history, has evidently entered a new critical stage in its evolution. The general crisis of positivism started, in effect, with the emergence of Marxist philosophy, its first real alternative, and has been aggravating ever since. It became particularly acute at the turn of the 20th century in connection with major discoveries in physics, mathematics, and philosophy, summed up by Lenin. New trials awaited positivism in the 1920s as a result of the emergence of quantum mechanics and the theory of relativity. No less troublesome were the subsequent periods of its evolution. All the storms positivism had to weather resulted, as a rule, in partial modifications of its philosophical program which took into account the criticism of its opponents, including Marxist philosophy. It is noteworthy that the representatives of positivism attributed all these misfortunes of their philosophy not to its intrinsic weaknesses or to their own fallacies, but regarded them as symptoms of a crisis of science in general. Moreover, all blame for setbacks and difficulties in scientific cognition they usually laid at the door of either materialism or dialectics. The strategy and the tactics of positivism fighting for its prestige in the scientific community evidently deserve special analysis which goes beyond the scope of our investigation. What we do need to emphasize here is the fact that it is not some particulars of the program of positivism that are called in question by the current scientific and technological revolution, but the very foundation of positivist philosophy. In point of fact, the revolution has completely undermined the scientists' confidence in the basic methodological principles of positivism: empiricism, conventionalism, indeterminism, the reduction of philosophy to the logic of science and to linguistic analysis, etc. The crisis of positivist philosophy manifests itself not only in the disagreement with science and its main tendencies but also in the emergence of new schools and trends within the philosophy of science coming out with sharp criticism of some positivist dogmas and proposing methodological alternatives to its traditions. The Western philosophy of science does not know a more radical critic of empiricism than Karl Popper. Critical rationalism as the methodological platform of Popper and his adherents does appear to be rather a formidable opponent of positivism. Its model of scientific cognition is essentially different from the positivist model, particularly if we take into account the views expounded in the latest works of the English philosopher, the recognition of theory as the most essential component of scientific knowledge, the deductive system of reasoning. Nevertheless, despite the apparent distinctions from the inductivist model defended by positivism, there is striking resemblance between the two models. Both of them postulate direct and simple connection between empirical knowledge and theory and assert the conventional character of basic empirical statements, if not laws themselves. Another characteristic feature of Popper's stand which seemingly distinguishes it from the positivist views is the recognition of the so-called World 3 or the world of objective knowledge. It is very significant, however, that Popper does not relate this world to objective reality, relying, like the positivists, on the intersubjective criterion of scientificity. His idea of objective knowledge borders on the idealism of the Platonic, if not Berkeleyan, type. Critical rationalism also differs from positivism in that it revives the principle of causality and shows special interest in the explanatory role of scientific theories. Yet even this difference is watered down by interpreting necessity implied by causal explanations in the purely logical sense a la Wittgenstein. The theory of regularity adhered to by Wittgenstein in relation to the problems of causality and determinism is obviously rooted in the philosophy of Hume and Kant and shows close affinity to the Machist concept of causality as probability of the expectation of consequences, as well as to the interpretation of law as functional dependence expressed by a mathematical formula. Besides the highly critical attitude to empiricism in the modern philosophy of science, the opposition to positivism also manifests itself in the understanding of the subject matter of philosophy. In this field the debates are mainly centered on the status of the so-called metaphysical problems. Critical rationalism does not go beyond the general legalization of such problems though they were implicitly recognized in positivist dogmata, whereas scientific realism, new ontology and new metaphysics, which have formed within the framework of the modern philosophy of science as alternatives to positivism, place special emphasis on the need for the restoration of metaphysics reduced to ashes during the anti-metaphysical crusade of positivism and make this issue one of the key points of their programs. As a matter of fact, the program of scientific realism boils down to the rebuilding of the scientific structure of the real world, the task considered to be worthy of philosophy. Very characteristic in this respect are the general scientific concepts and meta-theoretical problems which receive extensive coverage in the works of this school's representatives. They indeed regard their task in terms of resurrection. One gets an impression that scientific realism is completely unaware of the age-old traditions in the investigation of these problems and ignorant of the dialectics of nature and social development expounded in Marxist-Leninist philosophy, which has never lost interest in such problems as being the structure of matter, the interconnection of space and time, the forms of motion, the laws of the development of material systems, including society, and carried out fruitful investigations into the philosophical problems of natural science, social progress, etc. The attitude of the Western philosophy of science to these and many other problems is indicative of its confinement within the narrow limits of positivist traditions. Of course, attempts to start from scratch ought to meet with sympathy, and it would be hardly fair to demand of scientific realism, scientific materialism, new ontology, etc. that they consider these problems within the framework of more general philosophical issues and substantiate the new ontology with dialectical and epistemological analysis. However, any attempt to develop a sound ontology today without fulfilling this requirement is inevitably doomed to failure. Moreover, an ontology constructed on a tabula rasa basis tends to reproduce in a crude manner some ideas and concepts of old natural philosophy gravitating towards mechanicism, speculativeness, the Laplacian ideal of determinism, etc. It would fail to rise to the level of universal, truly philosophical generalizations and only strive to replace them by a more or less coherent system of general scientific statements. Such statements based either on biological and cybernetic ideas, or on the set theory and the latest achievements of physics would inevitably lose their concreteness and degenerate into truisms, leaving at the same time a lot of loopholes for idealism, the more so as they are intended to deduce the world from current scientific concepts and tend on the whole to petrify the present-day knowledge rather than to give a dynamic picture of living reality on the basis of a truly philosophical approach. Consciousness, too, with all its specificity and richness of content, is deduced from the interaction of molecules and atoms, whereas the mechanism of heredity in living organisms is viewed in terms of quantum transitions. The tabula rasa approach of new metaphysics to the problem of ontology will hardly enable the philosophy of science to raise the edifice of new methodology above ground level in the place of the ruins left by positivism. All attempts to revive ontology as a doctrine of the objective world and its most general properties and laws will at best remind one of a recapitulation course of history unless their authors turn in earnest to Marxist-Leninist philosophy, to the achievements of modern materialism that has assimilated all that was best and most progressive in the history of science and culture. It is for this reason that we set ourselves the task of familiarizing the reader with some principles of Marxist philosophy, showing the essence of dialectical materialism as an alternative to positivism and considering possible solutions to the present-day pivotal problems of methodology. It would be presumptuous to claim a more or less complete exposition of the views of the classics and modern Soviet philosophers in this book, not to speak of the elucidation of all the problems that have been touched upon in its polemical sections. The author has only singled out a few most acute problems which have become of late the object of particularly heated controversies and which have not yet been subjected to a sufficiently detailed analysis in Marxist literature with due regard for the nuances brought in the limelight. As regards the positive content of this book, we attach special importance to the problems of the scientific value of philosophy and of the concreteness of philosophical knowledge which are closely connected with each other. In Marxist philosophy, concrete knowledge has always been associated with the completeness of the reflection of objects and their diverse relations and links with one another. Conversely, the abstract has been regarded as an equivalent of isolation, particularization. Any statement represents a dialectical unity of both opposites, therefore there are no and cannot be any absolutely abstract or absolutely concrete scientific statements. Any scientific knowledge can only be more abstract or less abstract. Regarding scientific cognition as a living process unfolding in time and space, we maintain that this completeness of the reflection of links and relations is different at different stages of scientific investigation. Hence, we distinguish three different levels or forms of concreteness: empirical, representing direct, sensual perception of objects and phenomena; theoretical, concerned with inner laws, essential links, relations, and necessary features; and philosophical, relating to the most general properties and phenomena of reality, the contradictoriness of development, the diversity and the unity of quality and quantity, the material and the ideal, etc., as they are reflected in the human mind. Real philosophical knowledge reflects certain universal properties of the sensually perceived world and is in this sense empirically concrete. It reveals the most general laws and relationships of the surrounding world and is therefore theoretically concrete. As distinct from the knowledge provided by special sciences, it also defines the epistemological limits for the solution of one or another problem, i.e. the concrete form of the relation between the objective and the subjective in scientific cognition and, consequently, is epistemologically concrete. In point of fact, philosophical knowledge can only be concrete if it takes into account the place of a given phenomenon or the property it reflects in the general system of categories and laws of dialectics and materialism. Concreteness is demanded by Marxist philosophy of itself in the first place. The concepts of matter and consciousness are only regarded as concrete within the framework of the basic question of philosophy. The category of contradiction can only be concrete if it is viewed in the context of the unity of the phenomena under consideration. Dialectics rejects such notions as the opposition in general, quality in general, essence in general, necessity in general, etc., regarded as absolute entities. It demands that the opposites be only considered within the framework of unity, quality in relation to a given quantity, matter in relation to consciousness as its derivative, necessity in relation to chance, etc. Outside this philosophical concreteness, the categories of dialectics and materialism become nonsensical. The concreteness of these categories is the main proof of their scientificity. The specific form of concreteness of philosophical knowledge determines also its relation to the knowledge provided by special sciences. Philosophy does not stand aloof from them, it merges with the entire system of human knowledge and actively penetrates all the cells of this living intellectual organism. Conversely, no special scientific knowledge could be fully concrete without the support of philosophy, as positive sciences do not concern themselves with quantity and quality, matter and consciousness, the opposites in objects and phenomena, etc. It hardly needs mentioning that no truly scientific analysis would be possible under such conditions. Possessing its own form of concreteness, philosophical knowledge performs not only the methodological, but also the theoretical function in the development of science. It is not something alien to special scientific knowledge, but makes part and parcel of its system. It stands to reason that philosophical knowledge integrated in the structure of human thought usually loses its independent meaning or, at any rate, remains in the background. It serves the purposes of a special scientific investigation or some practical action and is entirely subordinated to it. This inconspicuousness of philosophical knowledge sometimes gives grounds for erroneous assertions that a well-developed theory has no place for philosophy at all. The history of science shows how philosophical principles and laws rise up in all their magnitude and reveal their power and viability in critical periods, at the crossroads of scientific cognition, when it becomes necessary to solve crucial problems of social and scientific development. Fundamental, theoretical sciences find themselves much more often confronted with such large-scale problems than do empirical or applied sciences, and it is usually fundamental theories that throw a new light on conventional, generally recognized philosophical principles. Hence, the cooperation between philosophy and special sciences is particularly fruitful in the sphere of theory. The attitude of theorists to philosophy is reverent and critical at the same time. THIRD relations based on mutual confidence leave no room for parochialism and, consequently, for petty squabbles over their share in the success of a scientific investigation or, conversely, their measure of responsibility in case of its failure. Here we have a single science whose only aim, untarnished by any prestige considerations, is to serve mankind. The question of the objectivity of knowledge assumes different forms and requires different solutions depending on the context. Philosophy provides the most general solution: everything that exists outside the mind is objective. Special sciences view the problem from a different angle, striving to eliminate the subject from the results of a scientific investigation. Empirical investigation does not know a more reliable means for obtaining objective knowledge than an experiment ensuring the investigator's neutrality. Theoretical investigation, in our opinion, pivots on the principle of invariance. In the theorist's language, the objective in the first approximation is equivalent to what is invariant in different systems of transformation. A natural scientist shows but little interest in the problem of objectivity in its pure, philosophical form, considering it even too trivial. His attitude changes when the problem comes to the foreground, e.g. when the former criteria of invariance fail, generally recognized theories collapse and the scientists need a reliable bridge to a new theory. Dialectics does not regard objective knowledge as a challenge prize which passes on from one generation to another. Objective knowledge must be gained by and for each generation of scientists separately and may only come as a result of their own labor. It should be extracted from the rock of subjective assessments, suppositions, and delusions, just like precious metal is extracted from ore. It is procured in arduous toil only to be rejected there and then and give way to more profound concepts and theories. In its approach to the problem of objective knowledge, dialectical methodology is characterized, first and foremost, by its constant striving to reflect all the complexity and dynamism of scientific cognition, avoiding any one-sidedness and absolutization of some particular methods or levels of cognition. At the same time, it firmly adheres to the principle of objectivity in its most general, philosophical sense, since the disregard of this principle leads to the erosion and devaluation of the entire system of scientific knowledge. To be sure, the concrete embodiment of the principles of dialectics offered by one or another scientist in his works may lack the necessary flexibility, completeness, or consistency. The blame for subjective weaknesses should not be laid at the door of dialectics itself. It provides a sound basis for the solution of problems facing modern science, the more so as it calls for creative approach to its own development.